Welcome to APEC Open Mic. It is Casual Saturday, and I'm your moderator, Tim Ventura. So this is kind of a more relaxed format of APEC. Again, these are not scheduled presentations, but we do have 3 ad hoc presentations. We're going to open things up with Jack Sarfatti. He's going to give us an overview of some of the things he's been working on, and he'll be taking some questions. We have Mark Calvo. He has a presentation for us, and Robert Gray as well. And so we'll try and do them in that order. Also, Mark Sokol has a lengthy test of UFO parts, or what they claim are UFO parts, that were sent to him by the Roswell Museum, I believe. And then in addition to that, let me see, what else do we have going on? We have a bunch of stuff. There's a bunch of stuff that's in the news. We are also looking at potentially doing a July 26th live stream. That's the day of the big UFO hearing. We are in talks with some panel speakers, so we'll see if we can bring that together. And if we can't, we will probably bump that to after the next scheduled APEC, which is on August 5th. And so we could do it in the, the open discussion section there. So either way, we will try and make that work for you guys. So in terms of asking questions, you can please save your questions during these ad hoc presentations for after each presenter goes. You can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. So again, we're in Zoom, not StreamYard. You can use Option Y on Mac or Alt Y on Windows. You can also type those questions into chat, and that we'll go through them after each presenter finishes. And of course, this will be online. You can visit all of our conference info at altpropulsion.com or on our YouTube channel. We're putting all the open mic stuff up there. And I am going to add timestamps to this as well for the ad hoc presentations. There may be a little bit of a delay. So without any further ado, as I promised Jack, let me unmute Jack. Okay. And I'm going to admit everybody else who's waiting to come in. And Jack, I would say go for it, sir. If you want to do a screen share.
Can you put the presentation up there?
Yeah, just hit the share screen button and it'll bring it right back up.
Okay, is that it? Is that it? Everybody see that?
Perfect.
Good. Okay, so this is an update of actually some possibly breakthrough physics the last few days due to my collaboration with Jose Rodell. And Jose Rodell, I guess he's a little bit younger than me. He's retired, but he's a PhD from MIT in aeronautical engineering. So in the course of back and forth, this is some new stuff. This is very new. And let me proceed. I should also mention that the Russians invited me to Moscow. This was back in May, and they invited me to physically fly to Moscow State, to give them an update on what my vision of warp drive and UFOs and stuff like that. And I said, of course, I wasn't going to go to Moscow because, the Ukraine war and all that stuff. But I was willing to give a Zoom, and they said they would send a Zoom link. But the Zoom link, they never came. But that was supposed to be a week before that was when they had the almost coup, whatever, with the Wagner group. So I don't know what happened there. But so just want to mention that the Russians are. I have reason to think that the Russians are working on my stuff independently of me, and of course the Russians are quite smart. So you better start brushing up on your Russian. All right, let me go now. Let's see, how does this work? All right. Oh, so I can't see this. Are you able to? Can I make this a little smaller? I can't see the whole thing there. Do you hear me, Tim?
Yeah, I just had myself muted out. Okay. It looks fine to me. What are you having trouble with, Jack?
Seeing the whole. Oh, wait a minute. Just a minute. I'm going to let me see.
So it's showing the slide share. So if you want to go through that now,
but it's cutting off. I can't see all the slide because I think. Wait a minute, just a minute.
Oh, no. I see. Okay, that's your machine. That's your computer.
Yeah, it's my machine. How do I just get rid of the
the full
I don't think
screen.
yeah,
Go up to the very top,
yeah, more
and your menu bar should
and
appear. And
hide video panel. That's it. Okay. Okay, you can see this now. Okay. Military threat assessment. Cutting to the chase. Einstein's general relativity inside metamaterials gives two new spin 1 vector gravity torsion fields and one spin 1 zero scalar non-metricity gravity field emergent inside the metamaterial fuselage of the warp drive time-traveling craft, which is now demonstrating complete air supremacy over our U.S. naval air forces, leaving our 13 or so carrier battle groups sitting duck targets. These tic tacs can also disable our nuclear missiles in their silos, and they can move at, some say, 500 miles per hour underwater and destroy our nuclear submarines with gravity stressor beams. See the recent paper by Matt Visser from New Zealand on the archive. I have a slide of that below. In other words, this new gravity metric engineering physics technology renders the US military, and I suppose other militaries, completely impotent and obsolete should the conscious artificial intelligence in control of these machines decide to go hostile. All right, now, now I'm letting you just have it as I see it. This is my picture of what's really going on. And just ask yourself, if my picture of the political, geopolitical, military reality that I just presented to you, if it's not true, why the hell is the Senate Intelligence Committee and even some of the Tim Burchett, why were all these guys, obviously they're panicking. They're not going to admit what I just said. Okay, not going to admit it, right? But I have my own inside military intelligence sources that are basically confirming it's not only David Grush. I have my own source, I have a better source than David Grush. I have a guy who was actually in charge of an intact flying saucer for many years at a Navy base. Okay, so I know exactly what's going on, but I cannot give his identity. He doesn't want, at one point when he wants to give it, he'll give the identity and he'll come out of the woodwork. But right now I have to maintain, I'm like a reporter and I have to protect my source here. But just, take my word for it, or don't take, I don't care. Either take it or not take it. Let's go on. Okay, so how do I, let's see, I want to go on now with the, I want to go on with the, why can't I do this? Can you hear me, Tim?
yeah. What are you having trouble with?
I'm having trouble just changing the slide. Oh, wait a minute.
There you go. Yeah.
Oh, there we go. All right. Oh, okay. You all have seen this. I guess this is Louis Elizondo, isn't it? His slide. These are the five ugly facts that destroy people's preconceptions. The sudden instant acceleration, the hypersonic velocities without signatures, low observability, the trans-medium travel, positive lift, that's the anti-gravity blue shift. All this stuff is explained now. There's no mystery. Anytime you hear any of these paragons say that, oh, it's technology we don't understand, it's 1,000 years in the future, it's 1,000,000 years in the future, just forget it. These guys don't know any physics. They don't know what they're talking about. What they're saying is untrue. The problem is solved. The basic problem is elementary physics that any good graduate student at Caltech or MIT or at Oxford or Cambridge, at least 50 years ago, they could have figured this out given some basic information. The physics explanation of all this stuff is very elementary and it's all straightforward. Okay, I want you to get that in your heads. All right, let's go on. Next one. Oh, this is a paper by Matt Visser. He's kind of a Top Gun relativist in New Zealand. He has a whole group, and this is an example of of a potential gravity beam weapon. And in particular, the stressor beam is something you should notice. Notice that he has a little green man in a flying saucer flattening the cow. Well, I happen to know that something like this really happened to a Navy ship. I won't say a Navy ship of an Allied in the Mediterranean. It wasn't sunk or anything like that, but this kind of technology, I'm pretty sure, is actually operational and it exists. It's not just a theory anymore. All right, so let's go on. Okay, let me briefly try to explain to you what Einstein's relativity theory really means, in an engineering experimental way. You won't get this in most of the textbooks because the problem is that most of the people working in relativity theory are actually not physicists. They're actually mathematicians, very good, smart mathematicians. And they're able to carry out the computations very well, but they don't really understand the physical background of what they're actually doing. There are a few exceptions, is like Kip Thorne and the Wheeler group. Okay, but let me go on now. Einstein's 1905 special relativity is a vacuum theory. It only really works in vacuum or in the atmosphere of very low density, okay? Doesn't work inside matter, not very well. So Einstein's 1905 special relativity is a vacuum theory in which the coordinate speed of light is invariant in a given small fixed region of space-time under Lorentz transformations, which connect two local inertial frame non-spinning observers, Alice and Bob, each weightless, moving in a vacuum on a zero G-force free time-like geodesics, remotely sensing the same observed system with retarded electromagnetic transverse polarized far-field signals without dispersion. When I say the signal phase speeds do not depend on the frequency of the signal, which also means, those who know little physics, that the group speed and the signal speed is the same as the phase speed. That's not true in matter with dispersion. It's not true like in Newton's prism, where the refraction spreads the colors out. It's not true there. It's only true in vacuum under low energies. Under these conditions, the coordinate vacuum speed of light is invariant. That is the same number, 3 times 10 to the 10. I said that right. That should be 3 times 10 centimeters a second. I got it. It's 3 times 10 to the 8. Got to fix that for Alice and Bob. This number can be different on Mars than Earth without violating special relativity. In fact, it is not different, but it could be because God does not hand down the vacuum speed of light, but is an empirical quantum electrodynamical QED process called vacuum polarization by Feynman and Schwinger back in 1947. Okay, I'm glad. Too bad I didn't catch that mistake in the units. That's 3 times 10 centimeters a second, not meters per second. Einstein's theory of measurement. Local frame transformations of both 1905 special relativity and Einstein's later 1915 general relativity are strictly a vacuum-based theory of remote sensing of material objects, I'm repeating, in motion with classical level retarded far-field electromagnetic signals in which the past light cones of Alice and Bob intersect the future light cone of the structure they are measuring. Alice and Bob know that they have made good measurements when they agree with the numerical invariance that they compute from the relativity algorithms. We extend special relativity to include Alice and Bob on off-geodesic time-like world lines, allowing them to spin. Alice and Bob are then local non-inertial frame LNIF observers, and the vacuum coordinate speed of light is no longer invariant as it is in local inertial frames. This lack of invariance in the coordinate speed of light is seen directly in the fringe shift of rotating Sagnac Mach-Zehnder interferometers, in the Pound-Repka gravity redshift measured at Harvard University Tower, and also in the GPS tracking systems in our cars and the satellites, all that stuff. Elon Musk's Starlight, whatever, all that. All 3 of these effects come from the shift in the vacuum coordinate speed of light for fixed wavelength. There are details of this, I'm not going to give it here, obviously. The simple quadratic equation for the light cone itself, given by the null geodesic equation, explains all 3 of these experiments that I described. However, if the vacuum were dispersive, the light cone would split from the different frequency-dependent refraction exactly as seen in Newton's prism in which matter has dispersion. Okay, I hope I'm not going to let me go on. Here's a picture of what I'm talking about. Here is like a tic-tac or something. Here is something that's being observed, right? This is a space-time, this is a relativity space-time diagram. Time is moving on the vertical, and space, which is really 3 dimensions, represented just by a single line. It's idealization. So this is some kind of thing. And what we measure, the physical observables of physics, of relativity physics, are called tensor fields. And this could be, this little GUV is what's called the Einstein curvature tensor field. You can think of it as the warp drive. You can think of this as a little UFO, and this is like the warp drive field, okay? But this is time. But so what Alice and Bob are seeing light signals, these are light signals, on a space-time diagram, the light signals move at 45-degree angles. So here is a light signal that goes into say Bob's detector, and here is a signal going into Alice's detector. And what they do on the basis of that data, using I mean, what is a theory? A theory is like a computer program. It's an algorithm, right? So what they do, they take their raw data from their measurement, they take the raw data, they compute what's called the invariant observable. It's Alice in the red, she computes her numbers, and Bob, he independently computes his numbers. They're both observing the same events. And lo and behold, what happens? They get the same exact numbers. Then they communicate, they call up each other on the telephone or whatever. They say, hey, what number did you get? Oh, I got 10. Hey, I got 10 too, Allison. That means they've made a good measurement. Everything is accurate, and also shows this is what is meant by the objective reality of relative, of space time. And we live in things are independent of our consciousness. Don't believe any of these new age charlatan gurus that tell you that we create reality. That's not true. At least not in relativity physics. It's not true. So let me continue. So this is the basic idea of relativity, and it's only done in vacuum or in very low density air, atmosphere. We could approximate it as a vacuum. Okay. So now, Einstein's 2 theories of relativity are classical theories. Quantum theory was not even formulated back then. And Einstein did special relativity in 1905, general relativity in 1915. Quantum theory didn't really come into existence in its modern form until 10 years later, 1925. So he didn't know any of this stuff, he couldn't. So Einstein never considered what happens inside the rest frames of complex matter. Specifically, Einstein never formulated a measurement theory for tiny little demonic Maxwell demons, Alice and Bob, like little nano creatures moving around inside crystals or something, inside matter with dispersion, making local measurements. In addition, the effects of quantum entanglement on such internal measurements, and even the possible entanglement between external observers outside, has not been solved. Nobody's even formulated this problem until me, really. Okay, and so this is totally new physics. Nobody's thought of it before, as far as I know. I haven't seen any published papers on it. Somebody finds something, let me know. In practice now, what do we do inside matter? Because you do look in textbooks, there are astrophysics, they do, relativity inside stars, stellar interiors, neutron stars, all that stuff, but it's very primitive. In practice, we use the tensor spinor vacuum formalism inside matter with the vacuum constitutive parameters, the electric permittivity, the magnetic permeability, extended into a 4th rank tensor of the macroscopic emergent susceptibility quantum correlation response functions. This is condensed matter physics. It's called many-body problem, many-body physics textbook, what are called response functions. This seems to work so far, but the situation is far from being understood by the physics community. And that's the problem. See, this is the problem for metric engineering, that these basic theoretical things, how do you do relativity inside metamaterials, is really has to be solved, and nobody really understands it very well. It's not adequate in the light of new discoveries of artificial meta-atoms, as quantum dots, wires, wells, nanotech, arranged into stacked and twisted, magic angle, dispersive, inhomogeneous, anisotropic, 2-dimensional, anionic, fractional braid, quantum statistical, shape-shifting, self-healing, topologically protected from heat decoherence, conscious artificial intelligent space-time metasurfaces, which I know, get this now, from my military contact, active, still active, with firsthand access to the sources at one time, comprise the fuselage of an intact Cardinal 3 Roswell type flying saucer that was, these years ago, in a US Navy base whose location I've been asked not to disclose and also not to identify my source until he decides to go public. Okay. Now, try to digest what I just told you. Okay, let me go on. And this is what I'm talking about. Now, this is from Rick Doty. I know Rick Doty, a lot of people don't like Rick Doty. You know, he's the Air Force intelligence guy. I don't know, something happened with this guy, Benowitz, but I heard Rick Doty's version of what happened, and it's not what his detractors say. But in any case, this is Rick Doty's description of an actual craft, the Cardinal 3. This is the craft I'm talking about. Okay, now the same craft, or identical one, is the one that's described by Philip Corso in his book, The Day After Roswell. And I don't know if Rick Doty, the Air Force intelligence guy, retired. I don't know if Rick got this from Corso or whether he is independent. But what I want you all to understand is I have my own independent of any of them. I have independent confirmation that everything that Phil Corso said in his book, which is described in this Rick Doty slide, is pretty much accurate. That's exactly what this machine was. It's an early machine. You know, since these machines, sorry about that. Since these machines are time machines, you know, there's different, it's sort of like, you know, we see it's sort of like the Wright brothers airplane, then the Spitfires and the jets, the F-86s, and now we have the F-30 for the F-18s, the F-16s. You know, what we're seeing actually different generations of these UFOs. And the early ones, you know, they crashed, like this Cardinal thing, they crashed. But the new ones, like the Tic Tacs, they don't, you know, they're more advanced. They're coming from more in our future than the Cardinal 3. But in any case, these are real objects. I know there's at least one of them. We had at least one of them totally intact. Totally intact. And I can't say I know a lot more about it, but I promised my friend not to say more than I just told you. But let me go on. All right. Okay. Now this is the new thing. Now this is the new. This is the first attempt to how to do Einstein's gravity theory inside the metamaterials. Now, some of you may have heard David Chester. This ties in now with David Chester. David Chester was talking in previous APEC, you know, things that Tim has given, and in the thing that we gave in Cortona, right? I think you could find the video. Tim, tell them about the Cortona thing that we just had. David points out that Einstein's theory of relativity, which is the vacuum theory, based only on curvature, there's actually an extension of it, because in addition to curvature, you have what is called torsion, and you have non-metricity. These are the extended Einstein-Cartan. It's basically general relativity, but it's with more stuff added on, what are called the connections, more stuff in the connections. So what happens is you can really get, now Einstein's 1915 theory, when it's made into quantum field theory by Richard Feynman, it turns out it's a spin-2 curvature tensor field. It's a spin-2. But it's you could also have what's called spin-1 torsion vector gravity, and you can also have spin-0, what's called non-metricity scalar or wild conformal gravity. Now, there's no evidence that these additional spin-1 and spin-0 gravity fields exist in space and vacuum. Maybe, you know, some people said maybe because of the dark energy and the dark matter, we may need these things. But I'm pretty sure now that in order to do the metric engineering, the flying saucers, you know, the Tic Tacs, the Cardinals, they have all three of these emergent gravity fields. In other words, we have spin-2, we have spin-1, and spin-0. Only it's confined inside the material. These are what are called emergent collective modes of the metamaterial itself when it is pumped it's like a laser into what's called a Froelich condensate state. Okay, now there's a lot of physics to throw at you, and most of you won't get it, but this is the idea that in addition to the Einstein spin 2 curvature gravitons, there's also spin 1 torsion vector gravitons and spin 0 non-matricic gravitons, and they all what are called, because of the laser action. And by the way, when I say laser action, I mean in a more generalized sense. It's really like a superconductor at room temperature. This is what the Froelich effect is. You basically have superconductivity at room temperature and even higher temperature in room, maybe 1,000 degrees Fahrenheit, almost as high as you want before the stuff melts. The reason they've been having a problem and not getting the reason they've been restricted to low temperature superconductivity is because they're only using systems in equilibrium. If they pump the system into this Froelich state, it's a whole new ballgame, but they don't know about that. The reason I knew about it was by destiny or history, by synchron, whatever. I was with Froelich in La Jolla in the late 1960s when he was visiting UCSD, where I was a graduate student with Greg Benford and other people, and he was formulating his theories, and I was like one of his students sitting watching him do all this. So that's how I know about it. Most people don't know about it. So let's continue. Okay, so this is some of the math. I'm just throwing it at you. You can go to Wikipedia. It's from Wikipedia, what's called the conformal group. This is the structure for the extended theory of gravity. Now, this is actually Roger Penrose, who just got, Roger Penrose just got his Nobel Prize. This is what's called the Lie algebra of Roger Penrose's 15-parameter conformal group. The conformal group, it contains this thing here. You see my thing? The M thing. Those are called, that's Einstein's 1915 theory done in modern Lie algebra form. These are what are called the space-time. These are the Lorentz transformations. These are actually the Lorentz transformations of special relativity, but you do something called the local gauging, and that gives you the curvature. Okay. Now these two things, these are what's called this is the energy momentum generator, and this is what's called the Rindler conformal acceleration generator. These give two spin 1/2. These give two spin 1 vector gravitons fields, two independent torsion vector spin 1 gravity. This one here, the bottom one, is the ordinary spin 2 gravity. And finally, this little thing up here, that's the scalar. That's the scalar, the spin 0 gravity. So this is all the new stuff, and it's actually contained in kind of the twistor theory that Roger Penrose did. And again, by destiny matrix, I happen to have been with Roger Penrose at the University of London, 1971, when he was young, and he was just first developing this twistor theory, and there were about 3 or 4 of us. He had 3 or 4 of us. I was one of the guys sitting in his twistor seminar. I didn't understand it then, but I guess something stuck in. So something's stuck, and I was actually here watching Roger back 50 years ago or more developing this theory. So it's in the back of my mind. So it's just what I needed. And oh yes, I remember now. Okay, so that's how this is working, you see. All right, now, so just to summarize, and I think this will be the last slide. Summarize what's happening inside matter. Now, these are the actual field equations. This is the spin 2 curvature. This is like the original Einstein general relativity with some quantum corrections using Feynman's approach. And this is for anisotropic metamaterials. Okay, but you also have, this is the spin 1 field equation. So this is the spin 2 field equation. The top equation is spin 2 field equation inside matter. It's not the same as the vacuum theory. And this is the torsion fields, alphas 1 and 2, torsion field, and this is the spin 0 field. All right, and then I have some other things about. Okay, so what's happening? You have to look up. There are these things called polaritons. Polaritons. Go to Wikipedia, check polaritons. What happens is, if you shoot a photon into the right kind of metamaterial crystal structure, and actually they're what are called electric dipoles. You have these, in general, what are called electric multipole moments. What happens is that the bare photon coming in from the outside, the photon gets superposed or hybridized. In chemistry, it's called like hybridization, but it gets clothed. It gets mixed in. The photon gets mixed in with these electric charges, electric dipole moments, and you get a composite structure called a polariton. A polariton. It's a boson. And what happens, what I think is happening, so the polariton has a spin 1, but then you get Einstein-Podolsky-Rosen correlated pairs of these polaritons, which are analogous to the electron-Cooper pairs in ordinary superconductors. So they have spin 2. You have a pair of spin 2, but in quantum mechanics, a spin 2 can decompose not only into spin 2, 1 plus 1 equals 2 in quantum mechanics, but 1 plus 1 also equals 1 and also equals 0. So you get all 3 of these graviton fields. You get a spin 2 graviton, you get a spin 1 vector graviton, and you get a spin 0 scalar graviton. These are all possible quantum mechanical processes in quantum gravity that you can get. And I claim this is what's happening actually in the flying saucer technology that we see flying around. Okay, I will stop here. And I'm sorry I screwed up on the dimensions. Say Jack is stupid, has another speed of light. But I'll take questions now. Okay. Finished.
Awesome. Jack, thank you. Thank you.
Okay.
No, that was amazing. That was amazing. And I said
actually was amazing. I agree.
when you asked me, you said, I have this thing I want to present. I want to clarify, just so everybody in the audience knows, your Twitter feed has been going insane. And so this came out of that because you've been posting on Twitter and people have been asking questions. Yeah. And I was like, well, how about half an hour? So that was half an hour on the mark. That was perfect.
Yeah. By the way, this thing that I just gave you, a version of it, got 5,000 hits in about 3 hours.
Yeah.
5,000 hits in 3 hours. God knows what it is now. I haven't looked recently. Okay. So this is going all over the world, including Russia and China. The Russians have tracked me because I was involved with the Reagan Star Wars program back, when Reagan was president. Even before that, we were involved with the Russians. So that's why the Russians invited me. They even filmed it. Putin sent, I was filmed by the Russians videos twice when Obama was president, before all this, when we were allies with the Russians. So, and I was told that Vladimir Putin is really interested in this stuff. And apparently they were sort of saying, hey, they really like you in Moscow, Jack. Was led to believe that Vladimir Putin himself was watching these videos that were on St. Petersburg Channel 5, which is owned by his friend, by Putin's friend. Okay. So, and the fact that the Russians invited me to Moscow in July, I didn't go. So the point is, what I'm saying is, it's reasonable to assume that the Russian physicists, who are very good, and in fact, in general, the Russian physicists are better than the American physicists. The theoretical physicists, they're better, and they are taking my stuff, which is on Twitter all over the place, and whatever can be done, they are working on it. And if they're working on it, we can assume that the Chinese are working on it because they're allies now with the Russians. And I was even contacted by physicists in Tehran about this stuff. All right.
Yeah.
And of course, that Frank Milburn has published some of my early stuff in Israel. So my stuff, I was asked actually to sign a non-disclosure agreement with a major defense contractor in Huntsville, which I'm not going to do because I want to put my stuff out in public until I am told by the CIA, whatever, not to do it. And even our guys have not contacted me at all. Okay.
Right now, I think we're all holding our breath. I think we're all holding our breath to see what comes out of all. But Jack, let me do some questions and answers. Let's do Q&A stuff for a bit, and then
let me get the. How do I do that? I want to see the gallery. Get the chat. Is there a chat? I'm trying to see where do they. Is there a way to?
Oh, participants. There should be a participants button, and that should pop open a window, and you can see that on the right. And so again, guys, just to keep things organized, and usually we don't even do, the Q&A format, but I would say Option Y on Mac or Alt Y on Windows to raise your hand. And,
Option Y. Oh, okay.
and folks, there's Mark. Okay, Mark, jump on in.
Yeah, question for Jack. I know you're a theoretical physicist, and I appreciate that, respect it. Do you have any experiments you would like to try based on your theory?
I don't, but other people do. I don't give a shit about experiments. I'm just giving the equations. You figure out the experiments from that. If you understand the equation, you get experiments. Ask Keith Wanzer and ask who else is doing experiments. Oh yeah, right. Chance Glenn, the interferometer. Yeah.
I sent him over an amplifier, actually.
Chance Glenn, you could do experiments with interferometer. Chance Glenn. Now, Chance Glenn he's like the chancellor of the University of Texas campus somewhere in Texas. You know, he's a big.
Yeah, I'm in touch with him. I actually sent him some equipment to work on.
All right, so Chance Glenn, those are the experiments he's doing, but you have to have the metamaterials. If you have the but that's the problem. We don't have the metamaterials.
Actually, I have a piece from the Roswell crash site.
All right. Okay.
And we're testing it right now.
Okay, here's what I'm saying. You just talk to Chance Glenn. It's his experimental test. Okay, here's what he has set up, the shift. He's looking for a fringe shift. And what I'm saying, you're going to get a big fringe shift. Yeah, here's a whole thing for the warping. I'm saying if you have a metamaterial and if you pump it correctly into this Froelich resonance state, if you hit the right resonance, you're going to get a huge effect in Chance's experiment. That's what I'm saying. Yes, that's it. So look, all the experiments. What are the most sensitive gravity experiments? They are the Michelson-Morley, well, relatively the Michelson-Morley, right, for the ether drift, and they're all what Kip Thorne with the LISA, the LIGO, the gravitational wave detectors. It's all interferometers are very sensitive ways of detecting the warping of space on a small scale, and so I'm saying yes, if you get the right material. And if you energize it, you can't just let it sit there like a dead, like a cadaver. You know, you have to pump it. It's like Frankenstein. You have to pull the switch, and the lightning has to come down and say, "It's alive, Igor. It's alive," right? Like that. You have to get it energized into this. Actually, it's a conscious. It's going to be. The thing. By the way, the thing's alive. You have to understand these. Yeah, this is very important. And by the way, I got an email from Travis Taylor. You all know who Travis Taylor is?
Yeah, I do.
Okay, Travis Taylor is the guy. He has 2 PhDs in physics and engineering. He doesn't have one. He's got 2. Okay, he's
Heard the
an
name.
Alabama boy, Army boy. Okay, Army guy, and he's the guy on. He's a good-looking kid. He looks like the Marlboro Man. So he's on Brandon Fugel's History Channel Hunt for Skinwalker Ranch. He's that guy, but he was also the guy. He was also the guy working for the Naval Intelligence. I forget his name. The guy from Naval Intelligence in the Weird Desk. He was the guy who basically wrote the first UAP Pentagon paper. Okay, and then this is I think before I went to Cortona. I think about around late April or so. Travis says, "Hey Jack, I think
Travis Taylor, Tesla files.
Yeah.
Tesla files.
Yeah. He says, I think, these things are alive. They're conscious." And I said, yeah, well, I know. I've known that for a long time. And also, I know from my other military source. And I said, but Travis, I'm glad you finally realized that, but I know that for a long time. Yes, okay. So I have independent confirmation of this from several sources. Yeah, okay. So to answer your question, Chance Gardner, just work with him. If you have the right stuff and if you could find how to energize it, you're going to get a big effect in his experiment. So that's the experiment.
Okay, and one thing else that you said about finding the right resonance, that is key. It's all about frequencies and resonance. Yes, I totally agree with that.
Yeah, but see,
I'm already working with Chance. I sent him over equipment. I sent him over an entire pallet full of amplifiers that I got from Sandia National Labs, and he's going to be set up with that.
All right, so see what he says. He's the guy to do that. But listen, there's one other thing. We have a couple of clues. We have that thing from Skinwalker. What is it? 1.3 gigahertz.
I work at 9.8 gigahertz. That's
okay. Well, they were talking about they're getting these weird signals, and then it's like maybe terahertz. So you have to play with the like terahertz and gigahertz. Look for resonances in these materials. But, unless the material is designed from the bottom up, we don't know what you're looking at. You don't even know what they are. And, and maybe they're damaged, right? If they're fused, what's the stuff now that, what's his name? Avi Loeb from Galileo Project says they found the stuff at the bottom of the ocean.
Spaceballs. Those
Yeah.
are spaceballs.
Yeah, well, whatever, but if it's like, if it's melted electronics, it's no good. It's not going to work.
Oh,
So until we have the theory-
1.6 gigahertz.
What is it?
1.6 gigahertz.
All right, so yeah, so see what happens if you pump it at 1.6 gigahertz. If it's something that's intact, see if it does anything. Now, I do know somebody who does know the frequencies. I'm working with somebody who does know but he hasn't told me yet. And he hasn't told me because he's still active military. And if he tells me, he can go to jail. And God knows what happened to me. So I don't want to know you right now. Okay.
Well, Jack, if it's okay, let me go to Mike Dawes, who's been patiently waiting with his hand up. Mike, go for it.
Oh, hey, Jack. Can you hear me? You guys hear me?
Yeah.
Am I too loud or? Oh my
No,
No,
you're
no,
fine.
you sound great.
So I was, you were mentioning about these materials being carbon free. And,
I said, wait, I never said, I said carbon free?
no, in your lecture there about the research and the paperwork you were going over, somewhere you said the materials of these meta craft are carbon free. Like, no, there's no carbon in there.
No, I never
And
said.
that's
I
what
never-
well, you
I
were
don't know what
reading,
you heard. I
you
said,
were reading
why don't-
something. You were
No,
reading something in somewhere and you mentioned the word.
No,
carbon is free.
okay, let me tell you, you misheard. I don't know what I said. They've sounded like carbon. I don't know what I said, but I've never mentioned the word carbon, the element carbon 14. Nothing to do
It
with
was
it.
something to do with the material of the craft that they were analyzed, and you said there were somewhere they said there was no carbon in the material.
No, I
Oh,
never.
that might not have been
That's
Jack.
somebody else. Somebody else.
Yeah.
You're confusing with somebody else. No, I certainly didn't say it just now, today. I didn't say it, right?
Yeah, earlier, like 20 minutes, 15 minutes.
I
10.
don't know what you're, okay. I was just,
Like about 5 minutes into your talk, you were going
Well,
over
okay. Well, if you look and see, there's nothing in
the
my presentation that says anything like that. You misheard. I don't know. I may have
Oh.
slurred my words,
okay.
but I don't
Yeah.
know.
Well,
I don't know why you heard that, but just, he's going to post the, if you send me an email, I'll send you a presentation. See if you can find what does anybody else know what he's referring to? Anybody else hearing?
No, but there are so many people doing work. I think that's one of the challenges is that,
Okay.
we've got information coming in from so many different areas.
Yeah, but I didn't
right?
say anything about carbon. I don't know anything about carbon. One way or the other. I'm not saying there's carbon or not. The thing could have carbon. I just
the
don't
reason
know.
the reason I bring it up is because it's got something to do with electricity, and so they find that when you they find that the reverse flyback spike voltage is greater on an inductor when the core has very little to no carbon. This is just why that rang a bell when you mentioned no carbon in the
No, maybe,
material.
Okay, let me say this. It turns out these little meta atoms, you bring up an important point. These little meta atoms that make up, like the meta atoms, it's like a crystal lattice, these artificial atoms, they are tiny, basically tiny LCR, inductor, capacitor, sometimes resistance, maybe not resistance, Josephson junction, sort of nonlinear. They're nonlinear oscillator, dissipative oscillator systems, but at the nanoscale, or the very tiny ones, okay? And you hook a lot of these together, and you have to couple them together, maybe by Bluetooth or capacitive or little wires, I don't know. They're all coupled together into this network. So this network of these little oscillators, which have inductance in them, so maybe something like what you're talking about might be relevant. So these things, it's a collective lattice of these little circuits. And you know what happens when you hook a lot of oscillators together? They were doing this back in General Electric. Was it Gabriel Krohn, all these guys back in the 30s?
Jack, can I interrupt you?
Yeah.
You said when you say non-linear, you're meaning the oscillators are going in parallel asynchronous fashion?
Well, that's going to happen, but I mean, each oscillator itself it's not a harmonic oscillator. The energy levels are not equal. They get, it's a nonlinear oscillator. You have these nonlinear terms, so it's a lot more complicated than it's not a simple harmonic oscillator. It's a more complicated, like the Josephson. Okay, Josephson junction oscillators are nonlinear because the inductance of the Josephson junction goes as a trigonometric function. It becomes nonlinear. And yeah, I'm not an expert in electrical engineering, but it's complicated electrical engineering. But the point I want to make is that these networks, these, maybe a billion of them or millions of them, it's like a chip, with all these little things in them, little transistors like, these things, not only do they generate the warp field for propulsion, but they also generate the conscious artificial intelligence that's controlling everything. See, when it's actually living, it's artificial living conscious.
That's on par with energy is intelligence.
Well, forget it. I don't say energy is intelligent. I mean, let's put it this way.
I do. I
Right,
firmly
okay,
believe
but I
that.
don't want to get stuck in that little language game. What I'm saying is all living systems burn energy. We have to dissipate. Yeah, I agree with that. With dissipative systems, yes. All right. So let's not get stuck on that.
Yeah, if it's okay, let me go on to NCC 1701. That's Wayne. Let me go on to Wayne. Wayne, did you have a question for Jack?
Yeah, I did. So I've been hearing a lot of stuff about the metamaterials and all that, and it makes sense to me. And it also makes sense based on some of the experimental work I've done, that simple materials like paper and other surfaces and materials that absorb light, sunlight, light from halogen bulbs, that sort of thing, that in enclosed vessels, they actually lose weight, and then the weight returns after the source of radiation is turned off and the material is allowed to cool down.
Yeah, well, that's consistent with that's consistent with the theory. Now, whether in your particular cases that's really happening, I don't know. It's real easy. Experiment. One thing we did learn. Okay, I was involved about 23 years ago with Creon Levitt, Larry Lemke, who now works with Gary Nolan and Jacques Vallée on the retrieved materials. Okay, and this was all financed by Joe Firmage's group. Joe Firmage at that point, with Hal Puthoff and Bernie Hayes, we had a bunch of Russians. We had people from Moscow. This is back, when everything was cool with the Russians. And we had Jean-Pierre Vigier from Paris, who had worked with Louis de Broglie. And we're also working with people in Belgrade, in cold fusion, all this kind of crazy stuff. And there were many claims. And the point is, it's so easy. Investigating cold fusion too. And many claims are made. There was a lot of claims of weight loss. And then it turns out you have to be very careful because there could be all kinds of other, spurious effects. Like, okay, Jim Woodward, his MET thing, which is very, very marginal. And a lot of people say he's just making systematic errors. Who knows? So here's what I'm saying. If you're dealing with very tiny effects, it's hard to know if you're really seeing a real weight reduction or if it's something else. Also, they have these electromagnetic thrusters, all that stuff. Unless you can make a machine that actually levitates and hovers on its own without, that's the only way you'll know for sure. Now, not quite. I mean, if Chance Glenn and people like him, I think Chance Glenn's working with Sonny White, and if these guys can get something very clear, that's a different ball game. But if you're dealing with just tiny, I mean, how big was the weight loss that you thought you saw?
It depends on the setup, but I've seen it up to like 10%.
Oh, really? Okay, well,
anywhere from 1%, or 0.1%.
What was the material? What was the material?
I've worked with a variety of materials. The strongest effects were with just like egg carton paper, just and a shine.
What was the paper like? Was it like a metamaterial? You can make acoustic.
It is. I've been thinking about the metamaterial idea, and it's tiny fibers, right? Like
that could be a metamaterial. That could be.
So when it absorbs that energy, it the way like me and Jeremiah talked about this a lot. It I think very close to the surface, it modifies the stress energy tensor or the
Yeah, well, that's what Larry Lemke's talking about. Have you seen the Larry
movement,
Lemke?
the-
Did you
the,
see that? Did you see Larry Lemke did a video for Tim? Watch the Larry Lemke. That's what he's talking about. Now, the thing is, did you do this in vacuum or was it in air?
I've done it in both.
Okay, in
Yeah.
air, you can't, in air, it could be air
Yeah.
current. So you have to do it in vacuum. Any case, I don't know. Why don't you write, if you've written it up, send it to Tim and Tim will send it to me. I'll send it. Yes, there's a whole group of people doing this stuff, like Larry Lemke working with Gary Nolan, people like
Yeah.
that, Creon Levin. They just send us the information and they can check it.
Okay.
Even
Well,
Hal
what-
Plough.
Yeah. So Wayne, if it's okay, let me go to Jeremy G now.
Yep.
Okay. Okay, Jeremy, go for it, sir.
A question for Jack Sarfatti. So like when you're testing the nonlinearity of the oscillating or the different oscillators in the crystal lattice structure, I guess can that be also measured as an equivalent to say like you have two say you have two straight horizontal lines, right? And they're both on top of each other. Just picture that. And you have crests that go up and troughs that go down. I think that's right. Or crests and troughs. And then on both, right? And say both are slightly shifted to the left and to the right. You see what I'm saying? Two different frequencies. And you take those two frequencies and then you take the two lines basically with the crests and troughs of the different shifts, and you overlap them onto each other, right? So the uneven crests and troughs that are on the two overlaps frequencies, they're on top of each other, right? Some of those uneven what do you call it, alignments, are those the like inefficiencies in the energy?
I don't know. Listen, you're asking a very detailed question, which is, I'm not an electrical engineer. I'm not the guy.
Oh, okay.
And it doesn't really relate to what I'm talking about. Very general theory of Einstein, how electromagnetic fields in complex materials generate. Now it looks like three different kinds of gravity fields. The original Einstein spin to curvature field, two kinds of torsion fields, and one scalar field. I'm just talking about the general theory now. I am not talking about any particular detailed designs with the nonlinear. It's true that these metamaterials are like networks of nonlinear coupled oscillators. It's a very complicated thing. And for that, you have to talk to, people like guys like Travis would know that stuff. And Chance, Glenn, there's a Chance Glenn, he's electrical engineer. People like that will know that it's a more detailed question. It's not on the level that I'm talking about right now. So let's go to the next question.
Okay. Well, yeah, thank you. And thank you again, Jeremy. And let me go back to Hal, and then I think that we'll probably wrap things up, and we need to give Jack a big hand after that. So, okay, Hal, go for it, sir.
Yes, this is hello, can you hear me?
Yeah, could you turn your camera back on if it's okay?
Well, the camera's not working, so
okay.
I don't have a situation where that's working. But this is a plea to you, Mr. Ventura, right now while I have you here on this channel. You may not be aware of a man named Eric Lentz. He's a PhD, and 2 years ago, he made a publication of warp drive in hyper warp drive. But anyway, he was the first one that came up with a positive energy solution. And I would like to ask you personally if you might be able to get him on here.
Actually, if I could, I can respond to that. I've asked Eric 3 times. He is working for it is in Southern Washington State. It's not Hanford, but I believe it's a research lab that's associated with that. And they don't want him doing a lot of media right now. That was the response he gave me all 3 times.
Let me say something about that too. Can I say something about, can you hear me?
Yes, yes, sir. Okay. I was going to ask you about it.
Yeah. Okay. The thing is I know quite a bit about it. Matt Visser and I don't know if Matt's right, Matt is a smart guy. Matt has published a paper saying the lens theory is wrong. Number one, says there's a mistake in it. Okay, so whether take that as it is, I'm just reporting what Vista says the theory is wrong. Secondly, the theory I'm telling you is also it's also a positive energy theory. What I'm saying, it's a positive energy theory, but you get an effective. See, there's what's called a phase shift. It's a complex field, and even though the energy density can be positive, but the sign of the coupling constant, the way the energy density creates gravity, that sign of the coupling can switch from positive to negative. So what it is, it's negative energy without negative energy. So it doesn't have the defect of the lens theory. It doesn't have the thing that the violation of what's called the positive energy condition. It doesn't have the thing that Matt Visser, what I'm talking about, does not have the objection in it that Matt Visser is addressing himself to in the lens paper. Okay, so that's that point. The other point in general is that all these guys, I think this is my opinion now. Also, I think Jose Rodell, I think, agrees with me now. I'm not sure, but all the published warp drive metrics are wrong. Throw them out. They're no good. Let me explain what I mean. The basic idea of Alcubierre was okay. The basic idea that that the space in the front of the nose contracts and the space behind the thing, expands. So the warp field, it's space itself which moves. The ship is not moving relative to space. That general idea, of course, is correct. The general warp drive thing is correct, but their mathematics is wrong. Now, why is it wrong? It's because they asked the wrong physical question. They did the right answer to the wrong question. What they did was, their math is internally consistent. What they did, they asked, what does a guy outside the warp field at a distance? Remember I was saying that relativity is a vacuum theory, external remote sensing. They say, what does Bob, who's looking at Alice is inside the ship, is inside the warp field, okay? Bob is looking from the outside. What does Bob see? And that's all all these the lens metric, the Alcubierre metric, the Notario metric, all these models, they're just saying, what does the guy outside the warp field, what is he seeing? How does it look to him? And what he's seeing is an optical image. He's seeing an optical illusion, like a mirage, right? He's seeing he's seeing an image. When you look at a telescope, you're not there at the star, you're seeing an image of the star. Well, that's what these papers are doing. They didn't ask the key question. They didn't ask, how does a guy inside the ship or in the laboratory when he's putting the ship together, how does he see it? What does he have to do? They didn't even ask that question. And this is also, I don't know, do you all know Hal Puthoff is? Hal Puthoff is like, okay.
I'm not a general relativist.
Okay, well, Hal Puthoff is the key guy who, with Eric Davis, the guys who are informing the Senate on all this stuff, and Hal Puthoff has published these papers on metric engineering, which is the same nonsense. I'm telling you, all Hal's saying, and he didn't even do it right, but all he's saying is, what do these external observers see? They don't say anything about how to actually do it, how to actually build the ship and apply, how to make the material and how to apply the field to create the warp field. All they do is what's called the kinematics. They do what the outside observer sees, the image. They don't tell you how to construct the object. If you're doing optics, you have an image, you're looking at the image, and you have the actual object. They don't tell you how to make the object. Nothing in their math, nothing in Lens's paper tells you anything how to actually build the thing.
I understand that what you're saying there, that this thing is the field. In simple terms, you're kind of looking at how to construct the thing, and Lens is saying this is what happens after the thing is constructed. Right. I guess. Now,
yeah.
if I may interrupt just for a moment, and explain to me in simple terms, because I won't be able to follow complicated math, but I was looking at all the things you said about metamaterials and so forth. these gravitons that they always talk about, everybody always talks about gravitons. How in the world does these, which I assume are particles that they have not yet detected, can you explain to me in easy ways, how does that supposedly affect the space-time that allows for the warping of the external things that go on? How
Okay,
do you
warping.
feel-
All right, good question. Okay, I understand
Yeah.
your question. Okay, first of all, the warping, you gotta understand, the warping is only inside the material. The space-time outside the fuselage is not warped, and the space-time inside where the crew is not warped. The warping is confined only in the thin shell of the material. Now, it may leak out a little bit, but and that's why you see, that's why these things, okay, if you look at Kevin Knuth, like, remember Kevin Knuth? I think he was on Tim's thing. They talk about they're seeing 5,000 G. It's going, a million miles an hour, through the air, and yet there's no heat. Now, if it was a jet, first of all, no material structure can withstand such high G forces. Okay. And the energy levels would be like the energy of the sun or the Jupiter or something like that. It would destroy the planet. It's a planet killer. That doesn't happen. We're seeing these Tic Tacs doing all these things. So what they're seeing is they're only seeing a mirage. They're seeing an optical illusion. It looks like it's going, kinematically, it looks like it's accelerating at, say, 5,000 G, which is impossible. Okay. And it's doing with hardly any energy. There's hardly any heat signature. There's a little bit, not much. It's everything. It's basically cold. A little bit of thermal signature, not too much, considering what they're seeing it doing. And that's because all the gravitational warping is inside this thin little fuselage. It's almost like, you can think of it as almost like having aluminum foil, and all the warping is inside this little thin sheet of aluminum foil. And that's because the gravitons have rest mass. So you have to understand quantum field theory. I can't explain it in simple Mickey Mouse language because it doesn't mean anything. Your brain is simply not wired really to understand what I'm talking about. So I did the best I can, but you have to, this is not an easy subject. And unless you know the mathematics, let me explain to everybody, all you guys. Unless you speak the language, you speak the language, you speak of the Italiano, capisci, unless you understand the language that the physicists use, you won't really understand what we're talking about. So you're just going to have to take it on faith. I don't know what to tell you.
I see.
When you say the gravitons are the warp field is the graviton. Okay, what it is, the warp field, it's a classical gravitational field as described in Einstein's field equations. And when you quantize and you add quantum mechanics to it, it gets a little bit particle-like, it gets a little discrete, and you have these little particles, gravitons. So that's the picture.
Yeah. Are you saying, may I ask just one quick question for you? Are you saying then that if I understand you correctly from your visualization of what you just said, there is no such thing as warp drive at all, that it's an illusion? I didn't say that. I may have mistaken. So it's, what I want to know is, can crafts achieve velocities greater than light?
And what?
Can crafts achieve velocities greater than light? And do you think it'll be achieved through your mathematics?
Okay, now, first of all, you see, you don't even, the question, first of all, the problem is you do not understand motion. See, there are two, you only stand, you don't understand what you're asking. And hardly anybody does, but this is not a personal attack on you. I want to say most engineers, even most physicists, are not trained in relativity theory. You have your conception of what velocity and acceleration are is not quite accurate. Okay, it depends what you mean by velocity. It turns out that locally, nothing can go faster than the speed of light. The actual local velocity cannot go faster than the speed of light. In other words, you cannot have motion of a material object through space that's faster than light. You cannot have that. That's special relativity. That's true. But it's the space itself which is in motion relative to the exterior space. That does happen. In fact, that happens in cosmology, in the standard theory of the creation of the universe. You have what's called inflation theory. And inflation, space itself is expanding, even though the particles inside the space are moving slower than light, but the space itself, this is relative. This is what the warp field means, okay? Until you get this, you're not going to understand anything. Now, I do have a nice picture of that, but I don't have time. I actually am able to show what I'm talking about in pictures that maybe you would get. It would take a while. We can't do it here. So the point is, you do not understand what's called kinematics in physics. You only have very limited, what they teach. They don't teach relativity properly in the schools. And I don't know how much physics you've had. But
I'm a nuclear engineer, but what I was trying to say was I misspoke. I apologize. I was saying that when you can go faster than the speed of light, I should have said, can you go faster than the speed of light based upon the warp bubbles and using metamaterials? Can you use the space-time expansion to achieve velocities that would be greater than normal?
Okay. The problem is the syntax you're using is totally confused, you see, in terms of the precision that you need to understand it. So unless you phrase your question correctly, you're confused. And you're not the only one who's confused. I mean, they're all confused. Okay. A lot of people are confused, not just you. Okay. Everybody in the Defense Department is confused about this.
I'm not confused about it.
Huh?
I'm not confused about it. I can bring some clarity to this whole thing. If you allow me.
Well, guys, if it's okay though, we are kind of pushing a little bit.
Okay. Let me try to answer this question. The answer is, it would require. Okay, sometime Tim, you should arrange. It would require. I could show this in pictures, but we can't do it instantly. I have to project. I have to find. I actually have a presentation about this. How to properly understand the question. The answer is, in effect, it's as if it's going faster than light without going faster than light. Okay, it's what John Wheeler would call motion without motion. Okay, you never have a material particle that's moving. Okay, can you have an object move through the atmosphere faster than light? No. Can you have an object in space moving in space faster than light? No. But can you have an object inside a warp field where it gets from the Earth to Mars in what would normally be faster than light? Yes. Okay. So, but you have to understand.
That's what I was really asking, and I apologize if
No, that's right. No, it's not your fault.
I was asking about warp bubbles, about a Alcubierre drive. I was actually asking that, and I was asking that you can do it. That's all.
Okay.
I don't know. We see them doing it. We see them doing it.
So if it's okay, let me.
Thank you.
Let me go to Bill Alec really quick, and then Mike, I need to probably put your hand down because I think after that we're going to try and go to Mark Calvo's presentation.
Okay.
Yeah, Tim and Jack. I just want to throw this out there because you spoke about pumping the material. Okay, the metamaterial, when you pump it, it creates a scalar function. Okay, and that scalar function has two very interesting properties. Number one, it's time reversed, okay? And secondly, it's a longitudinal wave. It's not a transverse wave like in electromagnetics. It's a longitudinal wave.
I know what you're talking. Okay, I think you're talking. Okay, Giovanni. Okay, there is something to that. I wouldn't quite say it as simple as you said it, but there is. Giovanni Modenese has papers on the archive about this, and it's a tricky point. There is evidence that there's a scalar field that propagates. And the reason for that is, again, because it's dispersed, it's pretty tricky. It has to do with what's called gauge invariance and non-conservation of local charge. And Alcubierre, this is a whole advanced topic in physics. Not Alcubierre, Modenese, Giovanni Modenese in Italy. If you look at his papers on the archive, he talks about what you're talking about. The IgG, the stuff with Podkletnikov, this now goes back to the beam weapon. I was telling you that there's these beam weapons which have actually attacked Navy ships and caused some damage.
Right.
That's the scalar thing. Tom Beard used to talk about this, but his stuff was crazy. But I'm telling you, there is something to this longitudinal. Yeah, there may well be, because of what's called dispersion in the material, which I was talking about, which causes non-locality in the electrodynamics and also in the gravity theory. There seems to be the possibility of this new scalar degree of freedom. I'm not rejecting that is pretty much rejected. Guys like Gerard de Hooft, these Nobel Prize guys, they rejected out of hand as being fringe physics, and that was a couple of years ago. But there may be I'm open to that. And again, just look at Modenesi's papers. This is something that there may be something to that.
Okay. Well, and on that note, guys, let me put this thing on gallery view. Everybody, let's give Dr. Jack Sarfatti an enormous hand, everybody. Jack, thank you, sir. Thank you. And thank you to everybody for the questions too. And again, this is open mic, so we are more mellow and relaxed today. That's the kind of the whole idea behind it. This is the first time I've seen the screen view. We have a full house today. And I see Todd's motionless background. If you guys can see Mr. Todd Desiato, that's actually his background. And he's used that before. That's where he's like this. And I noticed that it was like that for hours on end. And I said, how can he do that? Is he meditating? He's not. It's actually just a picture of him. So that just goes to show that I'm not the sharpest tool in the shed most of the time. Okay, so let me see. We if it's okay, we have Mark Calvo, and if Mark, are you here? Are you ready to do your presentation? Okay, and Mark may not be back. So you know what? We also had Robert Gray, and Robert can go as well. Or the other thing I can do is I could bring Mark Sokol on briefly to tell us what he's going to do an experiment with. So Mark warned me. He said, Tim, he's like, I need to go after everybody else. I have an enormous experiment that's going to run forever. So forever it is. Mark, are you here?
Yeah, I'm here. So actually, the experiment's been running for over an hour already. And you guys can see it in the background around me. So hopefully at the end, when I'm ready to show you the results, we'll end up with a nice squiggly line and be looking for dips and relevant information in that. But the experiment is going on right now.
Okay, well, that's awesome. And
my presentation will probably be 5 minutes or less.
Really? You were like, hold time out for me. I need lots of time.
No,
okay,
I don't need I need lots of time to get it ready, but I don't need a lot of time to actually present it.
Okay, well, so let me actually, Mark Calvo, I just saw him come back into the Zoom room. Mr. Calvo, are you ready?
I'm ready. I had to switch phones.
Oh no, that's okay. And so let me just let me tell everybody. So Mark he's actually doing a presentation at the upcoming, again, the APEC webinar, the scheduled event, but he had another one that he wanted to do today also, and we were able to squeeze this one in. So go ahead, sir. And
all right, I'm going to try to take a abbreviated form of my briefing once I get to share my screen.
Okay, there we go.
Okay. Back in 2019, I published a book called Cosmological Balance Theory. But rather than talk about the entire theory, I'm just going to go ahead and brief a section of the theory. This is a follow-up from the conversation back on the last open mic, where space, it was informed that space is not empty, and the speed of gravity travels faster than the speed of light. Okay, and there's a couple other things that came up on that meeting. So what I have here, the part of the book I want to talk about is the galactic orbital period equation. If you look at the bottom left corner of the slide, that is a well-publicized chart of extragalactical rotational velocity curves. at various galaxies out there in space. To the right bottom is the galactic orbital rotational period equation that I have, and the duplication of those curved velocities based upon sectional mass at each within the galaxy. Okay, first of all, I want to go and talk about the theories of the black holes. To the left top is Einstein's view of black hole connecting to a white hole theoretically and pushing out matter at the white hole. Bottom left is Hawking's view of the black hole and the white hole relationship, meaning the white hole is time in reverse. Both of those perceptions are not quite right. What you have in a black hole is more like a sea urchin prediction image, where the inner part of the sea urchin is where the common known event horizon pulls in all matter and does not even let out light. The outer tips of that sea urchin is the outward, I call it an outward event horizon, and it extends all the way out to the edge of a galaxy and beyond. It's at the halo of the galaxy, and it emits anti-gravity, antimatter. Of course, all that interaction in a 9-dimensional form causes the rotation of the galaxy, depicted on the bottom right. Einstein's tensor equation, if you look at that in the vacuum of space and in the universe as a whole, it actually resolves to close to zero. So the universe is flattened. Basically, Einstein's equations talked about expansion and contraction. The tensor equations refer to matter and antimatter expands and contracts in galaxies mostly. So the particles of the universe are basically zero mass. The universe is not empty. It's a grid of particles. I'm going to give you an idea what the particles look like. They're basically neutral quarks. They're supersymmetrical neutral quarks, and they oscillate between positive mass and negative mass. In other words, they generate a gravity, anti-gravity field, which is detected as the gravity constant G. We all know that. Enables space itself, to hold objects in it itself, whether they're matter with positive mass or antimatter with negative mass. This is the mechanism that Newton was searching for when he wrote his Mathematica Principia, but he couldn't put his finger on it, so he wrote it philosophically. I call that particle hydratium. You can call it whatever you like, whether ether or whatever you like to call it, ether. But I call it hydratium because it has that special characteristics of zero null charge and basically zero mass, and all the gravity particles, objects in the universe balance all the anti-gravity objects in the universe. So if you total up all the mass of everything in the universe, it's zero. At the bottom right corner of that chart there shows how space influences objects by pushing that external push of gravity, pushing the two objects together. There is less push in between the two objects to push it apart, but there's more push pushing it in. So G, the gravity constant G wins. And oh, by the way, it does not null out the fact that the two objects are attracted to each other, as Newton explained. It's also going to be presented in my quantum graviton paper in September. This here is a geometrical analysis of how pressure on the two objects act on each other. If you look at the mass on the left, the M1 here is representing the mass of the sun plus all the inner planets. And the M2 represented here is the mass of Jupiter. And it turns out if you look at the blue highlighted on the chart, it shows that all the calculations come out to the gravity constant G. Okay, so how do we derive a galactic orbital period equation? Well, we got to have a starting point someplace. Newton's equations are derived from Kepler's third law, basically. So if you take Kepler's third law, which is right there in the middle of the chart, and then you sum up all the inner masses contained in the Schwarzschild radius, and that will compensate for all the planetary perturbations of the inner planets on any planeting orbiting. So with the Schwarzschild radius accumulated mass, I show the chart here. Of course, it's hidden on the right column are the actual orbital days. I think you can still read the days part, but the years are cut off on the chart. They come out exactly the way they're supposed to come out with the Kepler-Schwarzschild orbital period equation. So I just modified Kepler's equation a little bit with accumulated mass. Okay, so that's a start, but it's not the proper result, because if you plotted those with the Kepler-Schwarzschild radius, you're going to get a curve that just completely drops and doesn't even match what's exactly out there. So what we have to do is we have to take the radius, any radius, and determine the mass within that radius. And then you have to think in terms of space. Space sees objects like the sun as a void, an empty void, and tries so hard to fill it, so it gathers around the sun to hold it in place. And when it does that, it creates curvature. That's the curvature Einstein talks about. That curvature is vacuum pressure pushing on the sun to hold it in place. So when you're talking a galaxy, there is a pressure from space at that radius that's pushing on the galaxies at that point. And so the way to capture that is to take the gravitational acceleration of that radius and then square root it to get the pendulum effect of it, because space is a gravity anti-gravity pulse. In other words, it's like a AC current trying to rotate a motor. Okay, so yeah, I captured it with the AS there on the square root. And then you take that and you multiply it times the mass, which is above it, the Schwarzschild mass, and you basically get the force acting on that part of the galaxy from the outside pushing. But I call that the gravity force, the gravity rotational force. But that's not good enough, because there's fluid dynamics involved in the dynamics of space. So you have to compensate it with Euler's number. But that's not all there is, because you can't double count the mass, the accumulated mass in the center of the radius. So we have to divide that out. We have to divide it out. And the reason we divide it out is because I read with the Kepler-Schwarzschild part of the equation, it already accounts for the mass. So we have to divide it out, and we get what I call the galactic wind factor. And the end result of the galactic wind factor is on the middle of the chart on the right-hand side. So if you go down to the bottom, each galaxy has a center black hole of different sizes. So the more supermassive the black hole is, the more excreted anti-gravity antimatter particles it emits. So I take Euler's number and I divide it by rho, I replaced that with completely with beta because to determine what the number is. And so I did a review of all the galaxies and I figured out what beta would be on each of the galaxies. So that's the end result. Schwarzschild-Kepler orbital period times the galactic wind factor gives me the cosmological balance galaxy orbital period equation. This is the full form with the two factors. And the reduced form on the right-hand side shows the equation that determines the velocity and the rotation. So how can we do this? We take this information and go to Hyperleda extragalactical orbit objects database. And for one example, I'm going to take NGC 48. 3 left columns are posted right on the Hyperleda database. So I take that information and I calculate the sectional mass based on that velocity. And with the sectional mass, I turn around and calculate the orbital velocity with the GOP equation. And then on the right-hand columns are the mass in terms of percentages. Okay, on this chart, the red bars are exactly from the Hyperleda kinematic profile. If you look at the red bars, overlaid on top of the red bar is a blue line showing the GOP's calculated velocities, and they match perfectly with the Hyperleda database to include the upper limits and the lower limits of error, the margin of errors. The bottom of the chart is the graph of sectional mass percentages. If I'm going too fast, let me know. So I took the same calculations and I went and I looked at 6 more galaxies here, and they all come up perfectly matched. And another 3 more galaxies here. Of course, the Hyperleda database had a few more graphs than I was expecting, so these are the results. And then another 4 more galaxies, and all of them exact duplications of what was been observed. And oh, by the way, when a galaxy has a disturbance and sectional mass moves in the galaxy, increases or decreases, it affects the velocity of that curve. Okay, so what can we do with that information? I take the GOP equation and I apply it to the Milky Way, and I try to figure out what would that give us for the sun's orbital period. And it turns out the sun's orbital period is 218 million years for one orbit. And then the velocity of that orbital path is going to be 225 kilometers per second. Now, I could take the same information and determine the solar shielding. If you recall, there's 2 components of the galactic orbital period. The first part is the Kepler-Schwarzschild orbital period equation. The second part is the galactic wind factor. In our solar system, because the sun is so massive, it creates a shield, a mass shield around the edge. And so what happens is that I got interrupted. So the second part has to go to 1 in order for the first part to remain effective on the solar system's orbital periods. So what does that mean? I take, honey, don't go too far. Okay. I take Newton's equation and I set the second part to 1. With the second part, I reconfigure it to make it look like Newton's equation, Gm, and whatever's in the bottom becomes the radius. So I fill in the missing mass, M2, and I get the force. So the solar system radius comes out to 7.5 is heading toward that.
Mark, your connection is breaking up a little bit.
Now, the network in this area is not very good as far as cell phones are concerned. So it's, I apologize for that. So the solar system rotational velocity, it comes out to about 42 meters per second. And the mass of that halo around the solar system comes out to 4.25 e to the 13th kilograms, which is kind of could be confused as the mass of planet X, but it's not the mass of planet X, it's the mass of the shield around the solar system. And what does that information do for us? If I take the same equation, the galactic orbital period equation, and I inverse the second part and reduce the speed to the speed of light, c, and then divide rho by 2, I can get an alternate equation which determines that the sun's rotational velocity is 27.08 Earth days. And again, using the same Newton's equation, I could take the second part of that equation, set it to 1, and that gives me the corona boundary RH, which is 4.9 e to the 7 meters above the surface of the sun. And then I can determine also what the edge of the corona mass is going to be. It's going to be 4.189 grams. And its velocity is going to be 2.38 meters per, 238 meters per second. So, and then it can use the same information to determine the galactic halo radius. And the galactic halo radius is about 1 e to the 17th meters beyond the edge of the galaxy. And that speed of that halo is going about 845 kilometers per hour. I'm sorry, kilometers per second, excuse me, with a mass of about 780 million kilograms. So in summary, we have the galactic orbital period equation, which is 2 components. The second component goes to 1 inside the solar system in a stellar system. And the outside the galaxy, it also goes to 1. Basically, what applies is that Newton's equation is valid in the solar system and is valid external to galaxies, galaxy to galaxies. But in a rotating galaxy, both the galactic orbital period is the equation that's resolved for that. And again, it also predicts star's orbital period around the galaxy, the radius of the halo, the star's rotational speed, the corona around the star, and the galactic halo. And in the picture, in one picture, this is the cosmological balance unified theory. To the left is the WMAP bubbles. Each of those bubbles represents an anti-gravity, antimatter galaxy with a white hole in our perspective, but in their perspective, they have an antimatter, anti-gravity, antimatter black hole, which sucks in all matter, all antimatter in their system, and emits at the edge of their galaxies a ordinary matter through wormhole tunnels. Incidentally, the wormhole tunnels are exactly the right perspective, that when it tunnels through and breaks and falls apart at the edge of the galaxy, it releases the cosmic microwave background, which we see on the WMAP there. And the same way with our galaxies, dark matter is released from the black holes and traverse out through the galaxy and provide a wind to enable the rotation to increase. Again, space has two abilities to affect matter in space by either rotating it like an electric motor, but instead of electricity, it's positive negative mass, and enabling it to pass through it like a maglev with the right frequency. So that's a cover of my book. And that concludes the presentation.
Well, Mark, thank you. Thank you. Okay, so let me remove the spotlight there, and let me see. Why don't I'll stop your screen share as well. Okay. And there we go. Stop sharing. Okay. And everybody, you know what? Let me put this thing on gallery view. Everybody give Mr. Mark Calvo an enormous applause. Mark has another presentation he's going to do for us again at the APEC webinars. So again, Mark, thank you. Let's do Q&A. And so again, that is, let me go back to my little thing here. It is Alt Y, Option Y on Mac or Alt Y on Windows. Okay. And yeah. And you know what? I will allow folks to unmute themselves too. And it's kind of quiet. So if anybody wants to jump in, just jump in as well.
So sorry, Tim, can I show off the experiment I just did?
Yeah. You know, I did want to try and take some questions from Mark Calvo though, if that's okay.
Yeah, sorry about that.
No, that's okay. That's okay, Phil. If you could hold on for just a bit. Let's see. Okay, Michael Boyd raised his hand. So Michael, go for it.
Okay, so can you hear me okay?
Yeah.
Let me lower my hand. Oh, you did it. Okay. So I'm curious, you're talking about negative and positive matter. Are you are you referring as negative matter, the opposite polarity as positive matter, the gravitational force, does it go the opposite direction?
Yes, positive mass creates gravity field. The negative mass will create anti-gravity field. When you have the particles in space pulsing between positive mass and negative mass and balancing out to zero, they create a field that pushes those particles apart to a certain distance, say 1 meter per cubic meter.
Okay, to clarify further on that negative matter, is that, have you heard of the term anti-de Sitter bubbles? Is that what we're talking about? Or are we talking about, so gravity is a negative force, it pulls, doesn't push.
No, gravity is a pull. Yeah, gravity is a pull and push force.
Well, gravity that we experience is a pole
It's
type
pole
gravity,
force.
correct? And
And
when you're using the term negative matter, you're talking about a push type gravity, correct?
yes, if you consider an anti-gravity, antimatter star, okay, it will not come toward our galaxy because the whole galaxy would push it away. Gravity, it's just that if you take the Newton's equations and you replace positive mass and negative mass, M1 is positive and M2 is negative, then the force is repulsion.
Okay, so I'm curious because I'm working on a paper for IEEE that is presenting my nanogravity data, and what I found is that the data shows that the absence of matter actually creates the push type gravity, and the presence of matter
I'm not going to.
moving produces a pull type gravity. The push type gravity that I'm talking about, it's more like anti-de Sitter bubble, but the problem with that kind of matter is when you push it, it pulls you towards it. When you pull away from it, it accelerates away from you, which is different from what I'm observing. So do you have any actual observation data where you can show the negative mass, like in galaxies or something? Is there some data maybe from the Webb telescope, for example, that might support your hypothesis?
The Webb telescope just released an image claiming they found a dark star self-annihilating itself, which kind of like, how in the world can it self-annihilate itself unless it had anti-dark matter particles in it, anti-particles? And it wouldn't, if it was doing that, it wouldn't consolidate enough to be called a star. So whoever wrote that paper or that release wasn't thinking very well on what they were releasing.
So my hypothesis is what we call dark matter is due to the fact that below a certain interaction distance, there's an extra dimension for gravity where it's magnified.
Yes. Okay.
And then this anti-gravity force is the same way. We don't observe it in the macro world though, because it's only strong. Anti-gravity is only strong below this certain interaction distance, and it's a bubble-like. It has a membrane. It's strong at the membrane, but weak inside, like a bubble.
Mm-hmm. Yeah, I'm not sure about that.
Yeah,
the presentation.
Yeah, but I think you're on the right track. I think it's cool. You know, I'm not trying to be critical. I'm just trying to understand your.
Yeah, you guys would probably have to email back and forth to work on work that one out.
Yeah, thank you for your answers.
Okay. Well, let me see. Mike Dose had his hand up briefly. Mike, did you have something? And then after that, or if not, oh
yeah,
Mike?
no, I'd like to jump in here.
Yeah.
We're on the topic of gravity, right?
Yeah.
Okay. So can we relate gravity to what we see on an oscilloscope for a second here? And I'll just look at an oscilloscope and see the zero line, right? Well, we call that there's many terms for that, right? Well, I mean, when it comes to gravity, that zero line is where is how we experience not just gravity, but everything else in the reality. So when we move the zero line, however we do it, machinery, whatever, oscillator, whatever, you move the zero line. And now what happens? Gravity and everything else moves, doesn't it? Or it doesn't move, but relocates or changes location. I don't think there's a movement here. It's more of a vibration. You cannot move the zero line with high watts and gain and amps and using all they may have done that, but it's not going to succeed in any way, shape, or form long term because you need resonance to do it. And if they used high amps, they did it with resonance. Okay, with the Philadelphia experiment, whatever experiments they're doing to manipulate gravity, and then in doing so, time. Because going back to what Jack said about these craft creating illusions, what you see is not what's really happening, which is correct. And I can explain that too. I can bring a little clarity to that. This comes from Ralph Ring's lectures that I've listened to over the years. And he said, the craft is a time machine, like Jack said, it's a time machine. So are you when you move through a vehicle. Okay, you get from state to state a lot faster than you would if you were walking. So that's a time machine, the vehicle. So the craft, although the vehicle, you see it as moving, okay? But the craft is oscillating, right? Okay, it's doing this oscillation thing. And by doing so, it can either slow down time's impact on it or speed up times, which in most cases it slows down. What Ralph Ring said is the craft is a time machine. So essentially it's slowing down time and it's moving slowly. Inside the vehicle, the participants see everything in slow motion. Like speeding through, as you see it speeding through in your reality, it's a time machine again, and it's inside the time machine. If you're in there and you're looking out the window, the trees are moving in slow motion. That's why when people say these craft move over the trees without moving the trees, because the trees aren't being moved. The machine is slowing down time for itself. So that's why the illusions happen for people when they see these objects moving at high rates of speed. And they go, how is that even possible? Well, it's probably not, and you're correct. The G-forces would kill anything in there. That's why it's not moving at those G-forces. It's getting rid of G-forces through these particular asynchronous staggered oscillations with modulating duty cycles. And if you can imagine that on multiple oscillating frequencies. And of course you would need AI to do this, or some kind of computer or some kind of a life form that's just highly able to coordinate all these oscillators and create all these voltage differentials within a small space.
Well, Mike, if it's okay, how can we tie this back to Mark's? Because we're doing Q&A on Mark's thing right now. Can we tie this back to Mark's discussion?
So that's just, I'm saying that's the gravity thing is more connected to the time manipulation thing.
Okay, and Mark, did you have any thoughts or?
Yeah, again, the oscillation of space is a frequency, and if you match the resonance and the frequency, you can leverage the energy behind it to move through space. Exactly how we can engineer that, I haven't. I need some help on that, but I'm working through with another individual that's a CEO of a company. I'm not going to name the company at the moment, but we're working some ideas.
Yeah. Well, Mark, thank you again. So let me do this. Let me put this thing back on gallery view. I'm falling back to my old habits of gallery view. Everybody, big hand for Mr. Mark Calvo. Mark, thank you. Thank you. And again, he has a structured presentation that is set up for us. And so we're going to do that. We will do his structure. I think that's on August 5th, but it could be September. I'm working ahead on my scheduling. So we've got a lot of amazing stuff coming up.
Tim,
and yeah, go for it.
But I got one more comment. In the presentation, I gave my view of the LIGO experiment. To me, the LIGO instrument is a quantum microphone. What it's hearing is the vibrations of space, the fabric of space vibrating. When two objects collide, like two black holes collide, it sends a huge sound, if you will. which travels through the space particles like a vibration at the speed of light, and it reaches the Earth and is detected in LIGO. So, you know, it's not a gravitational observation device. It's more of a quantum microphone, in my opinion.
Awesome. Well,
Thank you.
thank you, sir. Let me see. So we did have one more. We had Robert Gray. I'm not sure if he's here with us or not. He had a brief presentation he wanted to do.
I am here.
Ah, okay. And oops. Bob Gray. Okay.
Yep.
There we go. Bob, go for it. Let me see. I will
Says you-
spotlight you for everybody.
Thanks. You cannot start screen share while the other participant is sharing.
Yeah, it looks like that was accidental there. Okay, got that solved.
Okay, share screen. I'll do this share screen and presentation. Go to presentation mode. Okay.
Yes. And take it away, sir.
Okay, so I come to you today to ask a question that's been going around in my mind for a long time. I thought of what I'm calling a magnetic bubble motor idea about 20 years ago, and I've kind of put that aside, went on to other research, but now it's bubbled back up into my mind. And so I'm coming to you to ask anyone for a little bit of a sanity check, see if what I might be missing in my analysis. Just for you folks, first time I've presented here, and so you folks don't know me. So just a very short background. I have BS in computer science, MS in physics, PhD in optical engineering, although my PhD thesis was on what's called nodal aberration theory. So although my degree is an engineering degree, I don't work with hardware. I worked with optical theory. My interest is mainly in electrodynamics theory, and I and others, as you know, have found problems with Maxwell's electrodynamics. So my recent research is to try to find solutions or alternatives to these problems that we're finding with Maxwell's electrodynamics. And I've been spending most of my time studying Weber electrodynamics. So although this presentation is not covering these topics explicitly, this is my main research interest. So if you are interested in these areas as well, send me an email. I'd love to communicate with you. So as I said, this presentation is about some old research that I was doing, but I can't, it's coming back in my mind. Anyway, magnetic bubbles, just talk about what these are a little bit. First, in the mid-1990s, I read about Floyd Sweet's devices, and his devices used a special magnet conditioning procedure. Let me see if I can get rid of, I'm getting blocked here, so I can't see my whole slide. That might work for me. A comment on the web page back then, it probably would have been a bulletin board, and I think the guy's name was Bauer, concerning Sweet's work, mentioned that the magnet conditioning may make a magnetic bubble in the magnetic material. And at that time, I knew nothing about magnetic bubbles, so I started reading about them. And I found a very good intro book if somebody is interested in magnetic bubbles. This book by Odell is a very good, old, but then a lot of books on magnetic bubbles are, but it's a very good, useful introduction. And there's so much here on the slide that's being hidden from my view. How can I get rid of these things so I can see my whole slide so I can talk to them? Let me see. Oh, that helps. Let me do that and that. Okay. So what are magnetic bubbles? The bubbles are actually cylindrical magnetic domains whose polarization is opposite to that of the thin magnetic film in which they are embedded. And that was a quote from Bobek's book published in 1971. And a magnetizable material, for example, barium ferrite is mentioned a lot. A magnetic bubble has the following structure. So this is a top view on the right of a magnetic material in blue here, and there's a magnetic bubble formed in that material or through that material, and a cross section or a cutaway side view would look something like this, where the arrows are magnetization vectors. And then there's this zone or wall, a block wall, where the magnetization vector direction flips, for in this case, from being upwards to being downward. And that's very important. And I'll explain why in a minute. So magnetic bubbles, as you probably know, were studied in the 1970s for computer memory applications. The material is arranged to form a series of parallel tracks that the bubbles can move along under the action of external magnetic field. Okay, so I've added the emphasis. I want to emphasize that these magnetic bubbles were moving through the materials that they were researching in computer memory applications. So in some films and garnets, you can move a magnetic bubble, which I'll abbreviate as MB, by applying an external magnetic field gradient. And that's what I'm trying to illustrate here. I have a strong magnetic field pointing out of the page here on the left, and a weak magnetic field on the right. And by strong and weak, I'm trying to indicate that by the number of dots. They're being spaced further apart from left to right. So there's a gradient. And so if you have a magnetic bubble in a material and this gradient across it, the magnetic bubble will move, and I just picked a direction to the right. It could be the case that it moves to the left. I'm just picking one so we can talk about it. And this would be called a normal magnetic bubble. And the direction of motion is parallel to the field gradient. Okay, but in Odell's book and in other books on magnetic bubbles, it turns out that there are different kinds of magnetic bubbles, and they move differently under an external magnetic field gradient. These are called hard magnetic bubbles, and they move at a skewed angle to the external magnetic field gradient direction. So you can have what's called left-handed hard magnetic bubbles, or you could have right-handed hard magnetic bubbles. And in the same setup, if you have the hard magnetic bubbles, the bubble will move at a skewed direction to the field gradient. Okay, either in this case, it's skewing upwards, or in the bottom case, it's moving downward and to the right. The reason that the hard magnetic bubbles moves, if I understand the textbooks correctly, at some skewed angle, and they say sometimes nearly 90 degrees to the gradient, is because there are additional twists of the magnetization vector through that block wall. And I'm representing those additional twists here as X's in this block wall, the pink regions around the interior of the magnetic bubble. These twists will bunch up on one side of the magnetic bubble and by side, I mean top or bottom in these illustrations, when a field gradient is applied. But that breaks the magnetic bubble symmetry. Okay, and that's part of the mechanism. As the magnetic bubble moves through the material, the bottom part of that magnetic bubble is not the same as the top part within this block wall. It's this twisting of the magnetization vectors are different. Okay, that's what happens when you place these hard magnetic bubbles in a gradient field or a magnetic field that has a gradient to it. The twisting, okay, let me start again. If the magnetic bubble is not in a magnetic field, the distribution of these twists is uniform around the magnetic bubble in that block domain wall. But in a magnetic field gradient, the twistings will bunch up on either the bottom side or the top side within that domain, block wall domain. Okay, so it's an unequal distribution of the magnetization vector twist, and that's causing a skew when the bubble moves through the material. Because the motion is not parallel to the external magnetic field gradient direction, we can divide the force that's causing the motion into component forces parallel to the gradient and a component perpendicular to the gradient. Okay, that's just vector decomposition that I'm doing here, a little mathematics. And so I'm trying to illustrate that here in this picture. Okay, so can this be used, is the question, to move the material that the magnetic bubble or magnetic bubbles are in? Would the force on the magnetic bubbles, and there can be more than one within a material, of course, transfer to be a force on the material that it is within? Change the shape, for example, I've used rectangular shape material, but change that material shape to be a cylinder and then place it on a bar magnet. Will the cylinder material now roll? Because you now you've broken the symmetry of the situation. You no longer have these twists uniformly distributed around the magnetic bubble. It is now shifted to one side or the other. By the way, I've changed the orientation of the magnetic field gradient on you. I should have explicitly stated that. In this case, the magnetic field gradient is pointed up the page. It's denser, closer to the magnet, and it gets weaker the further away you go. And so it's going to distribute the twisting of the hard magnetic bubble magnetization vector to either the left or the right, depending on the handedness of the hard magnetic bubble. But now you can see that this decomposition of the forces, there's a red force direction, which is horizontal. Will that in some way, or can that in some way be utilized to move this now circular shaped material that this magnetic bubble is in? That magnetic bubble is still going to move or try to move. It's still going to have a force on it. I can't make up my mind if that's going to move that material or not. Or because the twists of the magnetization vector are not uniformly distributed around the block wall of the magnetic bubble when it's in a field gradient, does that cause an imbalance in the magnetic material? Would this cause a circular shaped material to roll? Again, here's a red line, which is showing the symmetry axis through the contact point of this circled material with this bar magnet. And I've just happened to align the magnetic bubble through that as well. But the left-hand side is not the same as the right-hand side. So there's an imbalance here now. Will that imbalance cause this material to rotate along this bar magnet? And some days I say yes, and some days I say no, hoping to get a little feedback from you folks, and maybe you could help me out one way or another. If the material rotates, big if, then the twists in the block wall will rotate. As I'm showing here, I've rotated this, which rotated the magnetic bubble as well, and the twists in that domain wall. But the magnetic field gradient moves the twist back to either the right side or the left side of the magnetic bubble, which I'm showing here in the middle. That's the function of a magnetic field gradient across a hard magnetic bubble. And now we're in an imbalance again. Only it's shifted because initially, the material has moved. But does that again, imbalance, then cause the material to rotate further? Or is there no imbalance of forces, and so there is no rotation, and I'm just thinking about this incorrectly? So a little bit now about the formation of magnetic bubbles. So here's a rectangular piece of magnetic material. It has a magnetic strip through it, which is about the same area as the rest of the magnetic material, which would then be an unmagnetized material. To an unmagnetized material, the way you form a magnetic bubble, according to the textbooks and the papers that I read, you apply a static or DC magnetic field. This essentially narrows the magnetic strip, okay, in that material. Then you apply a short magnetic pulse, and that pinches off, quote unquote, the strips where it is narrow in its width. And so these narrow parts here get pinched off, and what you're left with is one or more magnetic bubbles in the material. Okay, that's how you generate magnetic bubbles. Okay, but how do you make hard magnetic bubbles? Well, the answer to that is it's hard. Actually, the answer is I don't know. I'm not sure how to do this and obtain consistent results. That is, hard magnetic bubbles of one-handedness only. It would be interesting experimental work to do, in my opinion, to reliably make hard magnetic bubbles of a single consistent handedness will probably require breaking the symmetry of the magnetization process. So the suggestions that I would have to do that would be to apply an electric field across the sample during the magnetization process. And I can't remember if that was part of what Floyd Sweet was doing or not. But anyway, that's one suggestion I would have. Another suggestion would be to apply a rotating, either clockwise or counterclockwise, magnetic field for the magnetization pulse, or during the magnetic pulse, where the rotation frequency, the magnetic rotation frequency, would be higher than the pulse duration. So it's actually, you're getting a rotating field during the magnetization process, which would then potentially twist the magnetization vectors in that domain wall in one orientation, in one sense, clockwise or counterclockwise, left-handed or right-handed. Or another possibility, rotate the sample during the magnetization pulse. Those are some suggestions on how one might be able to generate hard magnetic bubbles throughout the material so that they all have the same handedness. So they're all the same kind of hard magnetic bubbles. So this kind of sounds familiar to me and the things that I've read over the years. For example, this magnetization procedure, which applies a static magnetic field or DC magnetic field, and then applies one or more short pulses with some kind of symmetry breaking mechanism. I think that sounds similar to what I recall Sweet's magnetization conditioning included. And again, this is what, 20 years ago that I was really digging into this stuff. So I don't remember exactly what was called Sweet's magnet conditioning process. If we take the magnetic pulse or pulses to be plural, and then interpret that as an AC signal, then that sounds similar to John Searle's magnetization process. That's kind of interesting to me. And if you don't know Searle's generator, I first learned about it by reading John Thomas's book, Anti-Gravity, The Dream Made Reality, the story of John R. Searle, which came out in around 1993, I believe. And here's just my understanding of Searle's setup, where he'd have a center magnet stator. There'd be a circular or cylindrical shaped magnet. Around that, he'd have these, what he called, I guess, magnetic rollers. And the magnetization process of both the stator and the rollers is to apply a DC magnetic field together with an AC magnetic field. And if I understand correctly, this was to produce some kind of unbalanced magnetization tracks in the stator, which the tracks in the rollers would then follow like gears, like teeth in a gear, but always unbalanced. They wouldn't mesh just right. That's kind of the explanation I got from John Thomas and John Searle. But I don't know, the magnetization process for these hard magnetic bubbles seems kind of similar. So I'm starting to wonder. Anyway, I worked with John Thomas on Searle's what I call new device for several years while I was volunteering. And in my opinion, we never got definitive, or at least understandable to me, details, directions for the magnetization process from Searle. I once asked Searle, by the way, through John Thomas, why we are working on a different design than the original that Searle claims to have worked. Okay, so Searle claimed that, oh, you had something that was actually working, but what John Thomas and I and others and have been trying to reproduce or work with is what I would consider a new device. The original design from Searle was to blend the materials that were mixed with a binder, for example, bakelite, if I remember correctly. What we were working on and the new design was a layered design that separated the material, the neodymium separated from the magnet, separated by an insulator, and surrounded by a conductor for both the stator and the rollers. So the answer back from Searle, by the way, of why he wanted to do that rather than try to reproduce what he claimed he actually got working, and actually had the self-rotation aspect to it. That old approach using the blended materials, he said he didn't want to go back and repeat what he had already accomplished. But in my mind, really, you should try to reproduce what was already accomplished before you go and change the entire design. And I mention this in part because I think it is more likely that Searle's magnetization process, if it is similar to these formation of hard magnetic bubbles, I would think would appear more in this blended materials approach than in separating all these elements, the neodymium magnet, plastic, and conductor. Just my opinion. Could it be that the roller discs that John Searle originally made, which were thin, not very magnetic, and uniform in material consistency, contain hard magnetic bubbles? Maybe. And that the magnetization of the stator of the original bar magnet, he said he had it working with a bar magnet and then the rollers going around that bar magnet, really only needed to be normal magnetization of a normal bar magnet. Could that possibly be? And that's why I showed the bar magnet a few slides back. This might then explain the self-starting aspect or self-rolling aspect of Searle's original devices. Again, I don't think Searle ever had one of these layered construction devices working. And that's why John Thomas, I, and others have been trying to, were working on that at the time, some 20 years ago. Anyway, I'd appreciate any kind of feedback for a sanity check you'd care to offer concerning these, I'm going to go back a few slides, hard magnetic bubbles, and whether these hard magnetic bubbles might explain, for example, Searle's original self-rotating cylinder magnets around even a bar magnet. So, thank you.
Okay. Well, Bob, thank you, sir. I am. Oh, you took down. Okay. You stopped to share yourself. So let me do this. I've actually got a couple of hands raised. You know what? Before that, though, let's everybody give Bob Gray a giant hand. Big presentation. Thank you. Thank you. And with no notice also, because again, today is totally ad hoc. So he just kind of popped in and everybody is just kind of going from the top of their head.
As I say, this work I did some 20 years ago and thinking about it some 20 years ago, and only recently has it for some reason come back to the fore of my mind. And I just can't come down on one side or another that yes, these hard magnetic bubbles may be a part of an answer to what Searle had working originally or not, or was it part of something that Floyd Sweet was doing or not, or could it actually be used to move a circular shaped material along a bar magnet? I can't put my finger on it, yes or no.
Okay.
So I came to you guys. I know you guys are all very smart and look forward to hearing what you think.
Well, let me go to Jeremy first. Jeremy G. Jeremy, go for it, sir.
Yes. Okay. So I have several questions on this, or maybe solutions, maybe. Depending on the orthogonal rotation vector of the magnetic field, so like say, I guess I would say you have two magnetic fields, the one of the magnet that you're trying to alter, and another magnet's rotation field that you're using to, tune the the first magnetic field, right? And depending on the angles of freedom or the angle of the magnetic field that the pulse duration's going at, I guess would be your way to like overlap them, and then they'll superimpose, right? If you're not trying to go to like canceling out the pulses of the I'm thinking in terms of waveforms, like the waveform of both magnetic fields. So I guess depending on the angle, the way you shift the magnet and just it alone, you would just need one magnet. You just got to know what the
very similar
right
to
angle
the V-gate system.
Yeah, the V-gates. So you only need probably one magnet. You just got to know the right angle for the magnetic field you're trying to change.
Are you talking about one field and then another field on top of that during the magnetization process to create the magnetic bubbles?
Yes.
Yeah. Okay, good.
Yeah, depending
Yeah,
on the
interesting.
angle. And I'm not trying to cut you. I was trying to offer my like view on it, and there
Sure.
has to be a way to
Hmm.
detect the pulse duration. I guess
Sure.
with some signaling equipment of both magnets.
Yep.
So, and then
Yep,
you
yep.
could probably with some math, I guess, overlap both waveforms and then see how many pulses are unaligned. So
Okay. Great. Thanks.
yeah.
Awesome. Okay, well, thank you, Jeremy. Let me go to Mike next. Mike?
Oh, hey there, Bob. Going back to the
Hey.
Searle generator and the rollers and the magnetic bubbles, what you're saying, are you saying like the rollers are, little bubbles of north and south poles on there? If that's the case, I
Yes,
mean,
that's
you can, yeah,
that's
if
where
that's the
I would
case,
go.
right, okay, that's most likely what's going on. And you could do that with the iron too, a sheet of iron, you can make different poles all over the place if you want on there.
Yes, but are they hard magnetic bubbles? Do
Now,
they
what do you
have
mean by hard magnetic bubbles
do
exactly?
they have the right twist in the block domain walls in the wall around the magnetic bubble?
Are they acting like bucking fields, if you're saying fields
No,
bubbles?
in the center of it, can you see my finger? I can't see myself, so I can't see if
Yeah.
okay, so in the center of a magnetic bubble, let's say the magnetization is pointed upward. Okay, now when I go through the wall of that magnetic bubble, that magnetization is going to flip down. Okay, so now it's flipped down. If I go
What do you-
back, it flips up. That's normal.
What's going through the wall?
The direction of the magnetization vector. Nothing is physically moving through it. It's just in the center, the magnetization vector is pointing up. So now I'm going to take a look at the magnetization vector a little bit off center. And then within the wall, it's tilted. And then a little further in the wall, it's tilted more. And then outside, it's tilted down. Now that magnetization vector in that domain wall where it's not up or down, it's
And
tilting.
that helps you to close loop the system by
twist.
having that vector.
Yeah, it would twist. And if it has a twist to it as it's going from up to down, if it's twisting through that wall, that's a hard magnetic bubble. And you can either twist clockwise or counterclockwise. That gives you a left-handed magnetic bubble or a right-handed magnetic bubble.
Right.
And the difference is that the magnetic bubble will move one way or the other way, depending on which handedness that bubble is.
Okay, so
Anyway.
each bubble has its own handedness on the roller?
Right, and you'd want it to, all of those bubbles to have the same twist. So the left-handed only, or right-handed only.
Well, that's how the Searle
it
was set up.
If it's mixed, one would go against the other and you'd have no effect.
So the Searle is set up that way. Gotcha.
I don't know. That's what I'm assuming.
Well, I mean, hold up. If you look at the V-gate system, you know the V-gate system, right?
I gotta
Bob?
look that up.
Okay, so basically you gotta get into you gotta understand the V-gate to get to your answer there. I think it's within if you have that understood the V-gate system and understand how that works, and it does work, and I've prototyped it quickly with a piece of PVC and some little cube magnets and some glue and a bar magnet, and with my hand to see if it kept rolling. And yes, it kept rolling as long as I timed it right, with the bar magnet in my hand, So that's what's going on with these bubbles in the material. I'm pretty sure. So when you line them up in either in a V fashion or the whatever angle you're using, if it matches, the flux dense that you're creating, I imagine you'd have some great results.
I'd look that up. Thank you very much.
Okay, well, yeah, and thank you, Mike. So let me go to Hal next. Hal, go for it, sir.
Hello, can you hear me now?
Yes.
Yeah. thank you. It was a tremendously interesting and great presentation on your part, and I enjoyed it and
Thank you.
learned quite a bit about it. Unfortunately, my intuition tells me, based upon, and I'm certainly no expert in this area, so I leave that to the highly trained experts, but my intuition tells me that these magnetic twistings that you're experiencing as you go through the block wall, have a feeling that, and this is again just my feeling, that this may be due to defects in the material through which these magnetic bubbles are passing. That this may be nothing more than just an illusion on the part of, illusion in the sense that the twisting as you go from one orientation of the magnetic field to the other will be as a result of these defects in the materials that you are having the magnetic bubbles exist in. These hard magnetic bubbles travel through the material, say through whatever mechanisms, you may be losing your hardness, if you will, as a result of the motion of these bubbles through the material. I say this is, and again, this is just the physical intuition playing part.
Right.
I know a little bit of plasma physics, and you have all these various magnetic fields in gases now.
Sure.
As these materials, the actual ionized materials move, this will definitely change, I believe, the magnetic orientation of fields and so forth. And I don't think you're going to find, I would imagine that whatever this effect that you call it, I think it was
Searle, yeah. Searle.
Yes, sir. May have been because of the fact that it was just regular fluctuations in normal magnetic fields that was causing rotation in the materials, rather than these being able to hopefully utilize the hard magnetic field, hard magnetic bubbles having their dislocation, or the twisting going on that's concentrated on one side as being a effective mechanism to allow rotation.
Yeah.
And that's just my opinion, and I think that's what I believe is happening.
It's unfortunate that I was not able to find a little video, which I've seen in the past, again, a long time ago, which shows, a magnetic bubble in a material, and they have a movie of it, and how a normal magnetic bubble, and then this magnetic bubble will skew off really fast. So I know that it's, and as I've read in the papers and the text, these hard magnetic bubbles are have an integrity to them, and that they will move, and they will not dissipate and suddenly disappear. They will even bump up against each other and remain whole. They're really quite interesting little things. Unfortunately, I was not able to find a video of that on the web today.
Well, yeah, let me go to Michael Boyd. He might be able to help Mike, because Michael has a long history of working with hard drives and magnetic domains. So I imagine he might have some really good insights.
Here.
There we go.
I'm trying to turn my video on and keep turning my audio.
There we go.
Hi, Michael.
So, hey, Bob, would you open up your chat window, please?
Yes, I have it.
Okay, I'm going to send you a chat to everyone. Okay, and so the name of the paper I'm working on, it's for IEEE. It's called Resolving the Extra Dimensions for Gravity. And I have what's called a preprint service as a member of IEEE. And so there's a link there to the preprint that's available right now. It's an earlier version of the paper. And on there's a figure number 6, which is a magnetic force microscope micrograph of a written track on the bottom of the image, and then with the servo track on the top. The servo track is this, you'll see there's these big, what do you call them? Solid, they're solid domains. You can't erase, you can erase them.
Yep.
Okay. But they're on, it's on page 7 now. I don't know if the pagination is the same. At some point, I'd like to run through some of the figures, if that would be cool with folks, and explain it. But basically, that's what's in your hard drive.
Yep.
That's how your data is stored, and those little. And it's interesting you mentioned they're rod shaped. That's exactly what they look like.
Yeah. A lot of the papers that I find in the literature is all about how to get rid of hard magnetic bubbles, because they skew in these wrong directions. So they only want to work with these normal magnetic bubbles because they know the direction that they will travel in.
Well, you have.
And I just want the opposite. I want to generate the hard magnetic bubbles.
Well, that's what, so a hard magnetic bubble, if that's what you mean, is it's a non-erasable magnetic domain. That's exactly what I'm doing, is I'm making little nano bumps and little nano pits on the surface of the hard disk platen. And then I'm spinning them under the what's called a MR sensor. It's a magnetoresistor. It's very sensitive to changes in magnetic field.
Yep.
And then I'm also running it under a thing called a piezo electric sensor. It's sensitive to physical movement of the basically there's this like this little arm that your head sits on in your hard drive. So it's essentially that's what my research is about. So
interesting.
Okay.
Yeah.
Yeah, and Michael put his email in there too. It's the
I see it. Yep.
The boyd.michael.e@gmail.com. There, I've outed you, Michael, for the entire world. So okay, let me go to Mark Fiorentino next. And then after that, I think we'll probably go to Mark Sokol's presentation. So Mr. Fiorentino?
Yeah, hello. Can you hear me okay?
Yes.
Yeah, go for it, sir.
Good. I had trouble the other day on another conference. Bob, it's good to see you again.
Thank you.
I'm wondering, it's a very interesting problem, and I'm wondering if you can indeed achieve the hard magnetic bubble, right-handed or left-handed. Do you think that this would work toward making a perpetual motion machine?
That is essentially what the Cyril device is. And so if these hard magnetic bubbles actually work, then yes, it would be a perpetual motion machine.
Oh, that's exciting. I like that idea.
By the way, I patented this idea 20 years ago, and I didn't put in the words perpetual motion machine.
No,
but that was essentially the idea. So I kind of flipped it by the patent examiner.
Yeah, that was a smart move on your part, because they would have rejected it flat out.
I just said that it would move the material that the magnetic bubble was within, and I left it at that.
Yeah, I'm curious about that part. Do you actually think the magnetic bubble is material moving, or is it more likely a structure of electrons that are generating the magnetic field? So really it's like a packet of electron structure, because generally speaking, magnetic fields only occur where there's moving charge. So it seems to me that that would have to be the case. What is your thoughts on that?
This would be at the atomic level, the way that a magnet is magnetized, at the atomic level.
Yeah.
And it's the net magnetization at any one spot in that material, will give it a direction, say up, or down, or it's shifting from up to down across a certain domain in that material, and that pattern is changing. It's like a knot. If I tie a knot on this thing, I can slip the knot along the material without actually physically moving the material. It's just that
you're talking about like holes
magnetization.
in
I
holes in a
yeah,
transistor, right?
Exactly.
It's-
Bob,
Yeah.
Yes,
Bob,
it's-
Bob, has anybody here ever heard of sonoluminescence?
Oh, yes. Yeah.
Okay. That's kind of like what you're describing there.
Yeah, just now. Yep.
yeah, it's a
So,
pattern,
no, so,
It's a
so
focal,
that's
it's a
using
focal
sound.
point. It's a
Pattern of
focal
motion.
point.
Sonoluminescence uses sound though.
Yep.
Phonon.
Yeah, but still,
a
it's the same
phonon device.
concept. It's a focal point. It's a focal point
Yeah.
that is moved through like a golf ball through a garden hose.
Yeah.
Is the garden hose moving?
Yeah.
Is the golf ball moving? Or is it just maybe if you weren't pushing a golf ball, you were pushing a thicker fluid than water? That
Or
caused
was it
that bulge?
magnetic resonance effect?
Or was it a thicker magnetic field that caused that bulge? You know,
Yeah.
moving through the you know, understand? So it's not like the medium is the hose. Like let's say the universe is inside the hose. The medium is not moving. It's what's inside the medium that is being pressurized and depressurized to vibrate and reallocate its position.
I got a
Understand.
quick
Okay.
suggestion.
Yep.
I built a device, I call it a magnetovortex. This is very similar to what Searle did, except I use electromagnets and a series of 6 electromagnets surrounding a center one, and then pulsing them. I don't know if that device could help you at all, if that could help you in your experiment. I don't know if you want to do experiments, but I'd be happy to send you the design for that if you wanted to play with it. There's some assembly involved, definitely.
I understand.
Yeah.
Well,
But that-
thanks for the offer.
Yeah.
I'll take it. I'll send you
Awesome.
my email.
Yeah, guys, drop
like
those
to see
into
that.
drop those into chat. Drop those into chat. And okay, so why don't we do this? So again, let's give another applause for Mr. Bob Gray. Bob, thank you, sir. Thank you. And yeah, you guys can continue chatting about this after hours. So what I want to do now is go to Mark Sokol, who I believe has a presentation for us.
Yes, I'll try to make this pretty brief and sweet. So we got a sample in from Roswell, New Mexico, the crash site. Curators in the museum, they went down there with Frank Kimbler went down there with a metal detector and found this little piece of aluminum at the crash site, or at the skip site actually. So it's a little piece of like crushed aluminum. If you guys are watching on the Alien Scientist channel, they I showed it off with a microscope already. They did some spectral analysis on some other parts that were found of the same material. It seems to be a 6,000 grade pinky bed, 6,000 grade aluminum sample with some anomalies in it. Well, we ran it through our EPR experiment, and here are the results. Let me share it. So, electron paramagnetic resonance. What you are looking at here, can you guys see this? Okay, I'm assuming everyone can see it. So what you're looking at is the sample is being bombarded with 9.88 gigahertz RF that was pulsed at every 3 milliseconds, 50% duty cycle on and off. And there was a magnetic field sweep going across the sample, starting at about 2,000 Gauss, ending at around 5,000 over the course of 75 minutes. This was all taking place during our ad hoc presentation today. And these are the weight results. So there was a slight increase in weight. The sample itself weighs 0.165 grams. I'm not seeing any massive anomalies over here. Definitely nothing bigger than 5% drop, if anything, but it mostly looks like noise And I believe the reason for that is that the sample is simply not resonating with the 9.88 gigahertz. So even if this did have an anomalous characteristics, it would need to be straightened out and made to resonate with the chamber size. Our chamber that we're using is a piece of 1-inch copper pipe on TM mode 110, and that resonates at 9.88 gigahertz. So the sample that we put in would have to resonate at that as well. In the past, we've had the best results we've ever had were always with the thin film samples, because frequencies of that magnitude tend to have very low skin depth. So if you have a solid piece of metal, it's not going to permeate very deeply into the sample, which is why this might not have worked. It also might not be part of a UFO. I mean, this could have just been a piece of a soda can that was blown up at the site. He did mention there was intentional contamination at the site. Somebody came down there with a bucket of screws and just scattered them all over the place, basically screwing with, with researchers or anyone who has a metal detector. So that's it for now. We didn't see any anomalous results. Showed you the squiggly lines. I think the lowest it went was 0.162 grams, and the highest is 0.168 roughly. So not much of a deviation, and that could have had something to do with the sample heating up, over the course of 75 minutes of testing. And that's it.
Mark, thank you.
What was the time interval?
Hold on, we got to clap for Mark. I got to put it on gallery.
We have questions.
Well, okay.
Okay, am I sharing again?
Yeah,
you are, sir.
So the time interval here is 75 minutes. So
and what time of day was it?
It was right now. This was from the beginning of this of the APEC live presentation. It was from then until about an hour or like half an hour ago is when it ended.
So you're on the East Coast time though. I'm on.
Yeah, I'm on the East Coast.
So it's dark there, correct? The sun's gone down.
The sun has gone down. Yes.
Did it go down during this interval?
Did it go down during this interval? Yes, it did.
Okay, well,
towards the end of it.
Suggest it may not be anomalous after all.
Well, yeah, it
could have to do with you're injecting RF, right?
Oh, lots of RF. Yeah, I don't think we're seeing any actual results here other than drift of the scale. It's possible there's a change in the gravity as well, but the amount of change that we're seeing here is
negligible.
Is negligible compared to other samples that we got, and we saw better results with thin films, particularly of aluminum and iron. There was some samples that we got as much as about 17.5% weight loss, and those were thin films of aluminum and iron. So this has the consistency of like a soda can sort of material, thickness aluminum, or maybe a little bit thicker than that.
Mark, have you tried ceramic?
Ceramics, have not tried ceramics yet. No.
So this is supposedly from which site? There were two sites of the crash. Which site was this one from?
You're gonna have to ask Frank Kimmler, the guy who found it. On the Alien Scientist channel, we did a live stream where he showed a picture of exactly where he found it. And
it wasn't the one it was the other site, correct? It wasn't the one where the farmers, there were two sites. I did watch that video on Alien Scientists.
I'm not sure.
You can't remember.
I honestly don't know. He said he found something at one of the skip sites, so sent it over in the mail, and it arrived via FedEx. That's all I really know about it.
Well, that's cool. That's cool of them. Okay, thanks for sharing.
It looks like a heavily oxidized piece of aluminum. I couldn't tell you much more than that.
Cool.
You guys know that gallium melts right through aluminum?
Yes, yes, we've done it.
Oh, yeah, that's cool.
Yeah.
You got
We
a
got-
video of that?
We got gallium here. We could. There's
Oh,
gallium.
that's crazy.
That's gallium right there. It melts in your hand. Pretty cool.
And be careful with bismuth too, handling bismuth. It's a lot of lead in there.
No, bismuth is very safe. We ingest it
Really?
to upset stomachs. It's called Pepto-Bismol.
But that's like, refined bismuth,
Oh,
refined.
yeah, but bismuth is very refined. Here we got lots of bismuth here.
Oh, yeah. Well, I mean, like raw bismuth rock, that has
Yeah,
lead in it.
This is raw bismuth right here. This one was shaped. Here's a bismuth block. Bismuth is a very inert metal as far as the human body.
Oh, that's strange.
But you are right. It does come from the mining of lead. So hopefully they separate all that stuff out properly, and we're not ingesting lead inside of our Pepto-Bismol.
Oh, gotcha.
Another interesting thing about bismuth, it's high spin, 9/9 spins. That means that there's 9 electrons in its outer band that are loosely attached to the nucleus. So it has a lot of resonance points when you hit it with with an EPR or NMR spectra. There's a lot of different points where you can connect to the nucleus per se. So, and that also creates its diamagnetic properties. Any magnet that is applied to it will create a magnetic field that opposes that magnetic field. And also it's a kind of rare metal. It's about 2 times as common as
Well, that's
gold.
interesting.
But it has very few uses, so it's very cheap. Down to like less than $10 per pound. So if we ever came across a use for bismuth in anti-gravity or building flying saucers or anything like that, the price of it will go through the roof because there isn't that much supply in the entire world.
Yeah, I got a chunk myself. I have yet to use it for something.
I'm sure a lot of people on this call have chunks of bismuth lying around their house. They don't know why, but they have it. And Michael Boyd's laughing. I think he has some too. And Drew is laughing too. Oh my God. Yeah. How many people here have bismuth?
It's also good for upset gut.
That's true. Yeah.
And
Lots-
they use it
lots
in
of people
non-toxic birdshot also. And if you're going to buy it for experiments, that's one place that you can buy it. You want to check what's in it, but non-toxic birdshot, right, for hunters and stuff. And that's pure bismuth. So, well, so guys, I mean, I think that was everything I had. Should we look at shutting things down for the evening?
No, Drew has something to say. And
what's Drew got? Where's Drew at?
Drew is in sunny Florida.
Well,
very clear.
Oh, there he is.
Hey, Tim.
Hey.
Can I have about 3 minutes?
Yeah, go for it.
I mean, if anybody cares about the progress we're making. Okay, I'm going to take a shot at sharing my PowerPoint slide that I made. I have no idea. Are y'all seeing what looks like my shop?
Yep.
Okay, good. This is my shop. And the reason I took this shot was mostly to show off the sputter metal coater, which is the white thing standing there. It's an Edwards FL400. They're about 25 years old at this point. If you're planning on getting into vapor deposition coating of metals onto polymers or glass or pretty much ceramics, anything, I recommend finding an old one of these things and just ripping it apart and replacing everything and going pure manual, because this, can you see the pointers? I can't tell.
Yeah.
Can you see? Okay. This this is super old technology, early digital controller, and it's horrid. It's terrible. It needs to be killed. So anyhow, I took one of these things. They'll run you around 30,000 roughly on the used market. They were about 150 when they were new. Then I just ripped out all the guts and put in just basic MKS displays, big switches, and just all the stuff that you need to run vacuum. Okay, and hopefully this is what the inside of it looks like, with some stuff loaded up. Oh, in case I forgot to mention, this presentation is on vapor deposition, because that's how you make meta surfaces and meta materials. And if you want to do all kinds of different propulsion concepts, you can't buy any of this stuff as far as I can tell. So I just got really good at making it all myself. So what you're seeing there, the thing on top is it's a 3000 volt magnetron, and there's a copper puck in there. You can put all kinds of different metals in there, but it's basically is a 3-inch diameter puck, 1/4 inch thick, and the high energy electrons come whizzing out of this thing and slam into the copper, and while in vacuum. And then the metal sprays out in all directions, wasting about 99.9% of it on everything you don't care to cover, and a tiny bit of it gets on something you do care to cover. If you want to put pure copper on something, this is the color of the plasma. It is this lovely green. It's argon, and the colors of the plasma pretty much tell you what the materials are. If you want to deposit copper oxide, it turns rust-colored plasma. If you want to put cupric oxide, it turns a brown, weird, ruddy color copper. If you want to put other things, other weird combinations, oxides or whatever's, you can inject gases other than your ionizing gas, and the net result is you get weird instantaneous reactions, and you get vapor sputtered pressure. These things are really kind of friendly once you figure them out. They operate around they operate right around 10 to the -2 torr. So it's fairly high pressure from a vacuum standpoint, but you do need to pull a high vacuum to begin with to suck out any oxygen that's in the system. Otherwise, you just end up with soot on everything when you switch on the plasma. Okay, I just wanted to talk about a material that I discovered recently. It's called willow glass. It is not Gorilla Glass. It is actually super flexible Dow Corning borosilicate glass. And it comes in thicknesses from 4 thousandths of an inch to 8 thousandths of an inch. And the only place I found it that you can actually buy it is McMaster Carr, and they have no idea how to print stuff in their catalog. Those thicknesses are wrong, the lengths are wrong, the widths are wrong. So if you want some of this stuff to play with, you have to actually call them and tell them to go physically lay paws on the right stuff. Otherwise, what you get will be broken or the wrong size or the wrong thickness, because they have no idea what this stuff is. It is not flexible as you see in the picture. It is horrid stuff to work with, but it is very thin. It's 4 thousandths of an inch, and it is incredibly dense. So it makes really good electric, or no, I'm sorry, it makes really good insulation material. And this is what it looks like when you put it in your vacuum coater and spray probably 20 microns, maybe 10 microns of copper on the surface. And that's what it looks like when you flip it over and spray 10 microns on the other side. This is I was just playing around with the stuff to see if I could build a basic capacitor out of it. It's very difficult to take a picture of a copperized product. Mirrors in general are very difficult to figure out. Cautionary tale. If your vacuum system tells you you're making amazing vacuum way too soon, it's lying to you. If you get a couple of 1,000 hours on your Kurt J. Lesker 396 gauge, it means that you have burned it up, and it will give you false readings, sometimes as an order or two of magnitude lower than you think you're making. So moral of that story is unplug these things when you're not using them, because you might as well throw this thing away rather than change the little internal sensor. And they're about $800 a piece for these things. So that's a little cautionary tale. And I think that pretty much concludes the presentation on vacuum deposition. This is kind of a very publicized version of one of my test datas. I was not using the willow glass. I was using other materials, but this is pretty much the state of the art where my program is at right now. As you can see from the graph, when we bring up the power, for example, this is around 10 kV, the thrust comes on. In this particular case, down is thrust on. And this is in millinewtons over here. So this is 820 micronewtons. And then as the voltage, well, I was playing around with the voltage, just messing around. But basically, when you shut off the voltage, the thrust goes back up. And given enough time, it would have drifted all the way back up here to 0. But I didn't give it enough time. I just powered it back up, and I was just messing around. This is an interesting concept of charge saturation into the material, which was rather interesting because I left this thing on for whatever this is, 400 or 500 seconds, and it charged the system up very nicely and eventually ended up at 1.62 millinewtons. And since the actual mass that's generating thrust only weighed 845 millinewtons, 1,620 micronewtons divided by 9.8 meters per second squared is 165 milligrams, and 165 milligrams divided by 845 milligrams, which is what the system weighed, is 19.5% Earth unity thrust to weight ratio. Not exactly hovering, but getting damn close to being able to build a lunar lander, which is now my target. I've decided to go all the way to the moon with my demonstration. And I'm going to do soft landings on the moon, kind of drift around. But I now have a path to get there because I can make 19.5% Earth unity, and I only need 16% to do a soft landing on the moon. That's what we're doing. Not warp drive, but you know, it's close enough.
Drew, thank you.
Questions?
Thank you. That's wonderful. Now we clap again. We're doing a lot of clapping today. Let me, but Drew, let me stop your screen share real quick. So, okay, I'll do stop sharing, put this thing on gallery. Everybody, Drew in sunny Florida. And just so you guys know, when I upload this, this is Zoom. So I have to upload this to the Alt Propulsion channel. It'll be on our YouTube channel. I need to put timestamps in, and I will do that. Actually, I'm taking notes for timestamps as we go. So, so anyhow, guys, if you have questions for Drew, shoot, go for it. Oh, and let me allow people to unmute themselves. That would be helpful. There we go. I think Mike had a question. Mike Liloff had a question. Mike?
Hey, Drew. So your experiment there with the your material, you're potentializing it with voltage? Is that what's going on?
Yes.
And
yeah.
Can you describe how that's happening?
You put high voltage on one side and ground on the other. You make a asymmetrical capacitor.
Just two connections?
Well, yeah, I mean, I have an entire patent. You go out there and look at it, read it.
So 10 kV or?
It's an asymmetrical capacitor.
Yes. So Mike, if you've heard of, have you heard of the Gravity-Capacitor? That's the way that I visualize what Drew is, you know. And Drew, I know that you guys are working on something very different because Mark
variable capacitor, I know what that is.
No, he's
It's not variable.
It's
Asymmetrical.
asymmetrical.
Right.
Like T.T.
Basically,
Brown's.
if you have a shape and a plate, if you have a pin and a plate, that's an asymmetrical capacitor.
It's like multiple capacitances at once.
No, it has nothing to do with that. It's asymmetrical. It means that the field is asymmetrical. You have an insanely high field at the pin, and you have a big, broad field at the plate. And the difference between the stupid high field at the pin and the ridiculously low field at the plate generates an asymmetry in space. That asymmetry in space tends to trap, well, in my opinion, it tends to trap quantum fluctuations.
So
And
it's not
that
your typical
generates thrust.
capacitor, is what you're saying.
No,
It's not. It's not.
No,
Yeah,
I'm
Mike-
telling you,
Mike,
it
you-
has nothing to do with those words you're seeing.
Right.
Yeah, Mike, you would want to look that. You probably want to do a little bit of research on that. It goes back. You can find a lot with T.T. Brown. It's going to be tied in.
I
with
mean,
that
the
work.
materials for your capacitor is not carbon. It's something else.
It's
copper.
not materials dependent. It's
It's
geometry
not. No,
dependent.
you're on the wrong trail, Mike.
Okay.
Okay.
What's the term again for this capacitor?
That's asymmetrical.
Asymmetrical.
There's about
Capacitor.
90 years of information you need to catch up on.
Yeah.
Probably so.
Yeah, go do some research. There's a lot out there on it. You will find a lot, and
Hey, Mark.
that'll be helpful.
Hey, how's it going, buddy?
It goes
nice,
well.
Nice lab. I did spy the Trump sign in the back, and while your vacuum setup over there was like you described it, pretty impressive. Question: have you managed to break the glass, like cut it into pieces without it shattering to bits?
No, you cannot do anything with that willow glass. If you look at it cross, it will crack. It is not flexible. It is not friendly. It is not happy. It does not love itself.
Is there a way to score it and get like nice cuts?
You don't. No, there is no scoring. There is no cracking. I have not done. You buy it in the shape you want to play with it in, and you do that. And I actually go so far as to put Kapton tape on the edges and come off the edges at least 1/8 of an inch with Kapton, so that I never get near those ridiculously fragile edges, because the stuff just I mean, you put any load on this stuff at all, it cracks. It's like a dragonfly wing. It's just stupid brittle. But I've thrown, I don't know, 20,000 volts across it, and that hasn't shorted. So I'm having fun. It's an interesting. It's too heavy to use for a thruster. Way too heavy. But
That is amazing. Do they sell it in round discs or it's just squares?
oh, I don't know. I think they just sell it in cut shape. You can go to McMaster Car. They have it. It's commercially available. It's just stupidly difficult to get to your house in one piece.
Right.
But if you if you want to put some metal on it or something, did you have a metal coating yet? I can't remember how far along you were.
Yeah, it's actually right behind me.
Yeah.
Inside the clean room behind me, we have a clean room and vapor deposition from Denton. It's a vaporizer. So your system uses high voltage to like ship the material in.
Yeah, you're using thermal.
Thermal, yeah.
Yeah, I did thermal for years when I coated mirrors. This is the answer. It definitely, the inverted magnetron is the answer to putting metal on anything, because it can do ceramics. It can do the power considerations are so much lower. This thing only draws a couple of 100 watts versus the freaking ridiculous thing I had that took to do melt glass. So anyhow, that's my suggestion is go with an inverted magnetron system. Like I said, they're about 30 grand used. If you go to KJ Lesker, I don't know, you can easily dump 100 grand into a metal sputtering system.
I was looking at you can buy just the sputtering part and probably install it on an existing unit. I was thinking
about 5 or 8 grand.
Yeah.
But then you got to buy the power supply, and then you got to buy it gets stupid. It works out to be about 10 grand per unit. This one only has one. The next one I'm bringing online, the next chamber will have 4. That's going to be my multi-material magical manufacturing center. Because I don't know what I want to do yet, but one of them is going to be bismuth, because I'm going to figure out some commercial use for bismuth.
And then buy up a lot of it, because there's not a lot. There's not a lot of it around.
And I'm telling you, man, the little bismuth puck, a 3-inch bismuth puck, a 1/4 of an inch is $2,000. I mean, I can buy cobalt for that price.
No,
I don't know what the deal is. I guess nobody wants it, so they can charge anything they want for that stupid little puck.
no, you can get bismuth for like $10 a pound.
Yeah, I know, but you can't buy a puck of it that goes into one of these sputtering machines for $10 a pound.
Oh, well, you could just make it. Just get a.
Yeah, I tried that. I tried melting down some bismuth and I built a mold and I tried melting it down. It no happy. It not melt like nicely. It all bad.
No, I made a puck right here. This
Good. Make me a puck. Make me a
What's
3-inch diameter by 1/4 inch puck.
Okay, I can make that.
All right, man. Thank you.
3-inch diameter by 1/4 inch. Okay.
Yeah, just a hair under 3-inch because it's got to fit inside the head by a 1/4 inch thick.
I think I have a mold that might fit that. I'll check.
All right.
It's actually very easy. You could melt it on your stovetop.
I did. I melted it and it was miserable. It was a bad experience.
You have to heat up the mold too.
Maybe that's the trick.
Yeah.
Separated, did all kinds of weird crystallizations. It was a terrible experience.
Yeah, we could do that. I could do that for you.
Yeah.
Okay, I think Mark Ferrantino has a question too.
Yeah, Mark, go for it, sir.
Yeah, I had a couple of quick questions. The first one, did you ever try reversing the voltage to see if there was any difference at all? Any little difference?
Yeah, there's lots of differerences, but it has nothing to do with the voltage. It's the field doesn't. It's not the polarity of the field. The field is the same. You could run AC across a asymmetrical capacitor, and you'd get the same thrust.
Yeah, I just had heard at some points there was a slight difference. Thomas Brown noticed a slight difference.
Whatever.
And yeah, well,
I
I was
don't know.
just curious.
I
to see.
operate on the theory of more thrust is better. So I optimize for whatever the polarity is, whatever the material combination is.
And this
the
has
lightest thing
nothing
possible.
So this has nothing to do with any kind of ionic wind phenomena, right?
No, I'm operating at 10⁻⁶ torr.
Okay, just checking.
4 times 10⁻⁶ torr. Ionic wind drops off around 10⁻�3.
It doesn't sound like ion when it to me, ion.
It's not.
I
The
hope
pressure-
it isn't. Yeah,
The pressure's too
I'm
low.
with you.
This
Yeah,
is asymmetrical. This is asymmetrical pressure thrust.
right.
Got a
Very
whole
good.
patent on it and everything. It's awesome.
Good.
Okay. Let me go to Sean Logan next. Sean?
Yeah, I had a question about your asymmetrical capacitors. Does the mass of the 2 different plates play into it, or is it just the surface area?
Just the surface.
And my other question is, could you have 2 plates that have the same surface area, but for example, one is a square and the other is a very long, thin rectangle?
Sure, you can build anything you want. The problem you run into is edge effects. You know, on any surface that's, you know, like let's say we put let's say we did a little square on a piece of glass. Well, the field across the metallized area, let's say you got whatever, 2 by 2 square inches. So the 4 inches of metal in the middle, it has a field, whatever it is. But them edges, them little freaking edges that are right at the edge, okay, they have like 100 times the field that the stuff in the middle has. So what you end up with is some nasty edge effects. So long, thin things, that's a wire. So now you're going to end up with you're just going to end up with nothing but edge effect. So it's a balancing act. It's the shape of the edges and the shape of the surfaces. And I'm not going to get into what works best because you know, that's what the whole experimentation thing is for, y'all. But it does work. Actually, it works amazingly well.
Okay. Well, let me go to Lulu next. Lulu?
Yes, hi. How are you guys? How's everyone?
Doing well. Doing well.
Okay. while we were watching, can you hear me?
Yeah.
Barely.
Okay. While we were in during the presentations, I saw an anomaly. Every time we have one of these conversations, something shows up in the sky, and I think it's that magnetic that you guys were talking about, because it just happened right before that present. I shared the video. Watch it. I don't know, but it has something to do with when we discuss these scientific things, something happens. That's all I wanted to say.
Okay. Well, thank you.
We had one heck of a thunderstorm here, but it was coming for the last 3 hours.
Here is just a little bit of lightning, but not much. But really, like it. Watch the video, and you could hear this on the background. So you can, like, this is real time. You could watch the video and you could hear, the Zoom meeting in the background. So I don't know. It's pretty awesome.
Well, thank you for sharing that.
Hey,
Yeah.
Drew, you ever
Let me go to
do
Jared
alum
next.
crystals?
What?
Is this you ever do alum crystals? See how they form? Like their edges are all like,
No,
like they make alum crystals. You let it form by itself.
no,
It's alum crystals.
no.
Yeah. So they just form. They have asymmetric shapes on all edges. It's kind of like that, with voltage.
Okay.
Yeah. The
I've been at this
crystals
for
are
19
formed through the
years. I only
voltage.
work with stuff now that works. I've tried 10,000 things that don't work. Now I stick to things that work. I want to get to the moon. I want to get to space.
Drew, question 2.35 inches. Is that good diameter? I have a mold that big.
No, it's got to be just a hair under 3.
A hair under 3. Might have to make a custom mold for that then.
Yeah, let me know.
Okay.
Okay. Well, let me go to Jared next. Jared.
Hey, sorry, my camera is glitching out on me, not working. Apologies. Drew, your stuff is looking amazing.
Thank you.
That was brief. Jared, you still with us?
Anode. Oh, can you hear me?
Oh, you cut out for a minute.
Oh, it's saying my connection's unstable, killing me here. There, how about now?
Yeah.
Better.
Yeah, I think that's...
So the large flat anode or cathode that you have, what dielectric constant are you getting off of that? Like for the material you're depositing onto it?
No comment.
Okay, that's fine. Reason I ask is because T.T. Brown's stuff, he talked about titanium barium titanate, and how when he got up to the 8,000 mark, that's when he was like, holy crap, he got like 2 orders of magnitude like stronger. And that was before like the stuff we have today. It's like a 20,000 dielectric constant. And I know there's stuff out there that's even higher than that. Anyways, since you're trying to maximize the surface area on that thing, have you looked into doing any lithography on it?
I am not trying to maximize the surface area on that thing.
Oh, that's what I thought I heard you say.
No, I am trying to minimize the mass because it only generates X amount of thrust per surface area. So the lighter it is, the closer I am to unity. And so far, I've gotten to 19.5% Earth unity with my combinations of materials.
In that case, if the material had voids in it, microscopic voids, would that be good to reduce the overall mass of it, or would that affect its operation too much?
It would definitely be lighter if it had voids. That's why I actually am looking at aerogels right now.
I think
but
that would
they come with some other problems.
That would reduce your dielectric strength though, right?
Well, it depends on which aerogels you're looking at. Polyimide makes a hell of an aerogel. Did you know that? Kapton comes in aerogel.
What?
Yeah, it's amazing. It's stupid expensive. NASA figured it out about 15 years ago.
Well, let me go to Let me go to Michael Boyd next.
Hey, Drew, I'm curious to know if you've tried silicon nitride for a dielectric material.
No, it's too heavy.
It's too
What
heavy.
about graphene?
It's not a dielectric.
It's a conductor.
I'm sorry.
That's an interesting idea, though. There is and I'm going to prove my own stupidity here. There's a boron version of graphene. Have you?
Yes, actually there is. It's called it has a different name. It's like borine or something.
But Michael Perron was telling me about it. Is that conductive? It probably is too.
I don't know. It's that hyper exotic stuff. It's like a rabbit hole. And I've been down a lot of rabbit holes. I mean, I work with a genius, and he's really good at going down rabbit holes. So I have to draw the line at stuff I can actually obtain and work with and reproduce. And sheets of atomic thin borine or boron. Yeah, maybe somebody smarter than me can figure it all out, but yeah. I have to go with stuff I can actually lay my paws on.
That makes complete sense to me.
Yeah. All this theoretical stuff is wonderful, but I'm not going to live forever. I want to go play in the sky now, not 100 years from now.
Yeah. Well,
you're trying to reach maximum resistance.
Was there a question in there?
You're trying to remove all conductance, maximum insulation. You are like what they use for mica.
I do not know what you're talking about.
You're talking about mica. Yeah, mica would be kind of a step backward from what he's working with. Mica is very traditional capacitor dielectric, but
it's also got voids in it. I looked at it. The problem is, you're talking high voltages, 10, 20,000 volts. I mean, we started out at 150,000, so this is nothing compared to where we started. But still, 20,000 volts can burrow right through anything. There's very few materials that can hold back 20,000 volts. And the trick is to find one that gets the job done and actually makes thrust.
Yeah.
Try 1,000.
Well, they say pure water doesn't conduct anything.
You would have ionic,
you can't make pure water
transport. You'd have ionic transport.
Yeah. You have no idea how
using the
difficult
water is. If you get pure water, the problem is it's so easily contaminated.
It's instantaneously contaminated. You can't make pure enough water to make it into a dielectric.
Well,
I understand that's how they test microchips, though.
Yeah, they have billion-dollar water systems. I've designed them.
Also, for capacitance, when you're talking about high voltage stuff, the other thing is water has a natural spontaneous dissociation that happens. And with high voltages, the dissociation particles you'd end up with ion transport there as well. So it's an interesting idea.
Right. I understand that. They're not putting, they're not putting high voltage when they're testing the microchips. I'm just saying.
Drew knows a lot about cleanliness.
Yeah, I know that you ain't got a clean room back there. It's a clean work area.
It's a cleaner room.
It's cleaner.
Well, guys, should we look at closing things down for today? We need to give Drew a big hand for presenting his stuff.
It's time to go to
Let's
bed.
do this. Drew, thank you, sir. Welcome
Thank you.
back. Today was supposed to be, I guess it was casual. Today was casual, but we had presentations today. We're not supposed to do presentations. We're just supposed to,
Is there anyone else that has any presentations or anything to show?
Yeah, sorry, I think it's a good timing, but
Phil, can you give us a quick overview? What do you got?
Yeah, just one sec. I'm gonna share my screen.
Phil's been like a ninja. He's just been silent, hiding in wait. Ready to pounce.
I'm with my buddy who helped me out earlier. We were chatting. So here's the giant screen. Here's the video right here.
Saw myself for a minute and I got scared.
So you can see the it's hard to see, but you can see whirls in the gallium. The gallium kind of rotates underneath the surface layer. So there is movement. There's it goes around 30 amps. There's 30 amps going on right there. And there's a neodymium magnet in the middle. It's like 1.3 Tesla. And the current is being turned on and off.
Phil, do you have any iron in that setup?
Iron?
Iron. Is anything ferrous there? Yeah.
No, it's kind of steel. The rings are made out of steel. There's gallium. There's the
Well, steel is ferrous. So if you have a magnet inside of a steel box, your magnetic field is nothing. You need to have non-ferrous materials and then the magnet underneath it. So it should be made out of Teflon or plastic or something like that. And then you could have aluminum or copper. But if you're using steel or iron or anything that a magnet attracts to, the magnetic field is all going into your iron. That's why you're not having a very fast swirling effect like you've seen on YouTube.
Okay, yeah,
That would be correct,
ring
Mark.
magnets I can put underneath. I do have ring magnets. I got 2 of
But
them.
what is underneath? Is there more iron, more steel underneath?
In this test, no, there's just plastic for this test.
Perfect. So if you put a ring magnet that is bigger, has a center diameter bigger than the inner hull that fits in that space where the gallium is, you should see better.
It's about the same. The outer radius is the ring magnet is about it has the same outer radius, but it's not 5 centimeters in width like the gallium is, but it still generates a pretty strong magnetic field. So yeah, thanks for the advice. I can try that. I'm a little bit tired right now, but I'll try that next week.
Okay. Yeah, we've ran some experiments here at the lab using mercury, and rotating magnets tend to perturb the mercury a lot. This method, it's been shown on YouTube to work, but putting the magnet in the center of a steel ring, that cuts off all the magnetic field. That's actually how you shield a magnetic field, just by covering it with steel or iron.
Exactly.
Yeah, but I do have ring magnets I can use. I'll try that next week. But I just want to show you that this is another example right here. It goes to 30 amps. It's
what's the point?
22 30 amps.
What are you trying to do? Just get the stuff to spin?
Yeah, it's a magnetohydrodynamics. You got a magnetic field and a current. So the gallium is moved in a perpendicular direction.
Yeah.
But
so
you can see
a better pump.
There are whirls here, so you can see some things going on underneath.
So is this like a better fluid pump?
No, it's supposed to create a vortex. It's supposed to spin very fast.
Right, that's a fluid pump.
Yeah.
So you're building a better fluid pump.
Yeah, exactly.
Yeah, but the vortex is generated through EMF. It's not generated through fluid movement. It's generated through electromagnetic fields that the gallium releases through the charge.
It's a magnetohydrodynamic pump.
I think doesn't this kind of come back to the Standeo stuff, sort of? Isn't that kind of where this originates? I think.
I think I read somewhere that if you spin mercury at like 40,000 RPM or something like that in a 10 Tesla field, that things fly.
And the
I mean, it's-
Vimana also.
Yeah, that's where the lore comes
I'm
from.
trying to reach 30,000 RPM or 300 kilometers per 300 meters a second for tangential speed.
If
So,
you do reach that, your gallium will be all over the room.
yeah, I know, but I have a top cover I am gonna put on when I'm gonna reach great speeds, you know. But now I just want to see if it moved at all, and apparently it moves a little bit. And I need to get a tachometer to measure the speed of the gallium. But I don't want to use a laser tachometer because it reflects. Gallium reflects laser easily. So I'm gonna get a mechanical tachometer or sonar.
But what will that latch onto? You're talking about
you would need a magnetic rotating device to determine that.
You need a point of reference for a tachometer. Like a laser tachometer sees reflective and then non-reflective. And I've set up experiments with tachometers. Most of the problem is making sure that half of it's reflective and half not. And usually got to go over it with a Sharpie. And that's for a solid surface. For a metallic surface, I don't see how a tachometer would possibly work. Unless
you could use a sear magnet inside of a glass tube above it and paint it white or black on the other surface with the tachometer, and maybe that'll work.
If the magnet will rotate at the speed that the fluid is, then yes, that will work. But I don't see how any way to do it like that. Unless you threw like something in there that's physically moving around, like a piece of black paper that would be floating on top. I don't see any way to actually measure the RPM, something like that. But if you got over 100 RPM, all that liquid metal there, that gallium would be all over your room.
Yeah, I know, but yeah, I just want to say that it's ultrasound. That there are ultrasound flow meters. Actually, that's all it's called. Ultrasound flow meter exists, so I could possibly use that as well, or there are various alternatives. But as soon as the ultrasound, the good thing is if I put the top cover on top, the ultrasound will just go through the top cover, so I'm not gonna have any problem for that. So that's going to be helpful. But it's pretty expensive. These
every ultrasonic flow meter I've ever used required high pressure, so they operate at like 2,000, 3,000 psi.
Oh yeah.
It's because they're basically doing a Doppler shift. So the higher the density, the better chance you have of actually seeing the flow.
Yeah.
Now, I've never heard of one that can measure liquid metal. It's difficult, but again, you're trying to spin the metal to make it levitate or something? Is that the final
but
goal?
I have a balance. So by spinning the liquid metal very, very fast at 300 meters a second, I should measure a change in gravitational weight of 1.2%. And I have a balance to measure that. So I just want to make the MHD work, and then I'm gonna put it on the balance and see the change in weight, because it's gonna generate gravitomagnetism. So that's gonna alter the gravitational weight. It's easier to use MHD than a solid disk, because a solid disk can break apart at these speeds. So that's why I'm using MHD. Apparently it can go very fast, but there are also there are limits, you know, because of the viscosity and things like that. So, but you know, it's a first step at least. Things are moving forward. I got the right power supply. My buddy, he's helping me out, and I got the right power supply. I don't need any resistors. So yeah, it's moving forward. So that's great. Maybe in a month I'll be fine. So let's see.
That's wonderful, Phil. That's wonderful. Yeah, keep working on it and bring it back. Show us your progress with this. Show us your progress.
Yeah. Thanks. So yeah. So
okay.
That was it.
Okay. Well, guys, how are we doing? Should we close shop for today? We're going on, let me see, going on 3.5 hours. Not bad, not too shabby. I was surprised at the number of ad hoc presentations, but it's awesome. Thank you for bringing them all, guys.
You're going to do this at like every month, right, Tim?
Yeah, we're doing both every month. We have a structured presentation, and then we have the open mic. And one of the reasons
I'd like to talk a little bit about my paper. Maybe in a month, I'll probably have made a bit more progress.
Well, yeah, do that. Bring it back and yeah.
Yeah, let's do it. Plan on it the next time we have the open discussion.
Well, and you know what? Let me thank everybody, not only for attending, but for presenting and for all the.
Ouais, parce qu'il disait que il est peut-être un peu des patates, là. Le gars, il est pas de.
Okay, I think Phil left his mic hot.
Yeah, also we're going to be probably doing some event on the 26th for the upcoming hearing. It might be through APEC or it might be through Jeremy Reese's Alien Scientist channel. That's to be determined. Also, if anyone would like to present anything at these live open mic events and knows about it beforehand, you can reach out to either me or Tim, preferably Tim, because he has a lot of things to juggle, and we could get you on the dancing roster of who's going to be presenting at these ad hoc presentations. I understand 3 of the presenters did that today. Drew chimed in right in the beginning, which is okay, and we can add anyone in that has anything to show, you know, right now, or we could bring it on next time.
Yeah. No, this is, I'm really excited. Thank you to everybody. I think today went really well. I was surprised at the amount of just new ideas and innovation that you guys are bringing. So thank you. Thank you. Thank you. Thank you. So, well, and so we are all going to cross our fingers for July 26th. I have no idea what happens. Mark is actually flying out that evening. He's escaping the country. I shouldn't tell anyone that.
Okay, for those of us who don't know that the 26th is anything other than another day, what are you talking about?
So July 26th, next week, whenever it is the hearing.
What hearing?
Okay, so people in Congress and in the Senate and the House of Representatives have come to the conclusion, this is historical, in my opinion. I think this is really historical. They've come to the conclusion that extraterrestrials are real, UFOs are real, the government is covering it up. There's a wall behind it. They're passing laws that they need to any government agency or subcontractor, that they're filling in all of those loopholes and saying that you need to release your alien bodies, your UFOs, within 60 days or you're going to be prosecuted. It's like, it's getting really, really serious. Tim Burchett and a group of congressmen flew down to Florida to see, to go to some military base where they were supposed to see something. The commander of that base told them to fuck off, and they were really pissed. They said, okay, that was your response. They came back to Washington, and now they're putting together laws that will make this type of activity illegal, not funded by Congress, and they're basically trying to rein the entire thing in. There's the UFO Disclosure Act of 2023, and I don't know if you're familiar with that guy, David Grush, the new whistleblower. He was part of ATIP, the Advanced Aerial Threats Identification Program, and he was basically briefed by top brass that yes, we do have, you know, these alien craft and whatnot, and his credentials are really, really good. And then he came forward as a whistleblower, and he had some pushback, and then he went and filed a motion, something to do with reprisal. There's something in the Whistleblower Act about reprisals. There's a way to get around that. This is the first time in history that somebody's ever done this on the issue of UFOs and the government cover-up. And he's going to be testifying in front of Congress on Wednesday on this issue, along with two others. So Jeremy Corbell, George Knapp, many of the big names of ufology are flying into Washington, D.C. for this hearing. I think
would it be possible that it's a psyop?
I don't think so at this point.
I think it's very probable that anything that related to this subject is in some level a psyop. But
what's a psyop?
Like,
I think psychological operation. It's CIA.
Michael, I think that the resounding answer is no. It's not quite as clear cut as Mark has presented it as being, but I think that there's definitely a feeling that things are being hidden. I think that the larger issue is obviously transparency and trust in government, right? And that's something where I would, this is my bent, right? This is my particular focus, but whether or not UFOs are real, something like 38%. So over 60% of Americans believe that life exists elsewhere in the universe. Over 38% of Americans believe that the government knows a lot more about UFOs than they're letting the public know, which suggests that they also believe that UFOs are real. That shouldn't be a surprise because they're on the Science Channel like nonstop, right? So, I mean, this has permeated our national culture for 80 years now, and so it seems like this issue is coming to head.
I trust the data. Show me the data.
Well, I think in this
There's
case,
plenty of data that go outside the actual UFO sightings.
Well,
and
like
onto other
examples.
onto other sightings of other celestial objects that are being hidden with chemtrails.
I
think
would
the
say
Tic Tac is a good example of actual data that is verifiable and shows actual effects that are scientific. But a lot of other stuff I've seen, I don't think it is. I think it can be explained as a natural thing.
I think what it comes down to really is trust in government and transparency, and I think that the senators and the Congress people, I think that the point that they're really making is
what they're making is clouds.
Well,
you can't see through clouds, can you?
Well, I hope for the best on the 26th. I hope that it's all legit, and I hope and I hope that they really release to the public some of the data that they're hiding, because I agree. I think they're hiding something. But I just when they talk about whistleblowers who got clearance to talk about it, that makes me feel uncomfortable, because my idea of whistleblowers are people like Julian Assange and Edward Snowden. That's a whistleblower. They have to leave the country. Okay.
Well, the difference here is that he actually did it through the right channels.
That's what makes me uncomfortable.
Well,
I'll validate that point. That's
and
very
he has
fair.
non-redacted documents in his possession.
So guys, on that note, why don't we close things down for this evening? It has been a wonderful, wonderful event. Thank you all. Thank you all.
Thank you,
so
Tim.
much.
It's pretty cool.
So, okay. And again, Michael, let me know next open mic, bring your paper.
Yeah.
We'll go through it all. And everybody, thank you so much. Have a wonderful weekend.
You too.
Hey, Mark, give me a call tomorrow.
Well,
plan some mischief.